dark flow, an intriguing and deeply perplexing phenomenon in the realm of cosmology, refers to the unusual and seemingly coherent motion of galaxy clusters. These vast congregations of galaxies, instead of drifting randomly as one would expect in a uniformly expanding universe, appear to be moving in a specific, common direction. Observations made by the Wilkinson Microwave Anisotropy Probe were among the first to hint at this anomaly. By studying the subtle temperature fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang, astronomers could measure the peculiar velocity of galaxy clusters, their motion relative to the overall smooth expansion of the universe. What they found was a surprise. A significant number of these clusters, spanning a vast region of the sky, seemed to be streaming towards a particular point, a direction roughly aligned with the constellations of Centaurus and Hydra. This was not a small or a localized effect. It was a large-scale bulk flow, a cosmic river of galaxies that did not seem to have a clear gravitational source within our observable universe. The implications of this are profound. The standard model of cosmology, which is built on the cosmological principle of a homogeneous and isotropic universe, predicts that on the largest scales, the motions of galaxies should be random, with no preferred direction. The existence of a large-scale, coherent flow like this is a direct challenge to this fundamental assumption. One of the most tantalizing and also most speculative hypotheses is that this dark flow is the result of the gravitational pull of structures that lie beyond our observable horizon. The universe is about 13.8 billion years old, which means we can only see the objects whose light has had time to reach us in that time. The universe itself may be vastly larger, perhaps even infinite, but our view of it is fundamentally limited. It is possible that just beyond the edge of what we can see, there lies a colossal, and as yet unseen, concentration of mass, a supercluster of superclusters, a vast cosmic continent that is exerting a powerful gravitational tug on our local patch of the universe, pulling the galaxy clusters towards it. This is a mind-bending idea. It suggests that our entire observable universe is not an isolated, self-contained system, but is just a small and gravitationally influenced, part of a much grander and largely invisible cosmic structure. This has led some to speculate even more radically. Could the dark flow be the first, tentative, and circumstantial evidence for the existence of other universes, for a multiverse? In some theoretical models, our universe is just one bubble in a vast, eternally inflating space-time, and collisions or gravitational interactions with other nearby bubble universes could, in principle, create a large-scale directional flow in our own. While this is on the very fringes of theoretical physics, the mystery of dark flow is so profound that it forces us to consider even the most outlandish of possibilities. However, the existence of dark flow itself is still a matter of intense scientific debate. The initial measurements from WMAP were subtle and at the very limit of the instrument's sensitivity. Subsequent, and more precise, measurements from the Planck satellite have not confirmed the original WMAP results with a high degree of statistical significance. Many cosmologists now believe that the initial detection of dark flow may have been a statistical fluke, or the result of a subtle and not yet fully understood systematic error in the data analysis. The universe is a messy place, and the task of disentangling the faint primordial signal of the CMB from the complex, and often much brighter, foreground emission from our own galaxy is an incredibly difficult one. It is possible that the apparent large-scale flow is not a cosmic phenomenon at all, but is simply an artifact of our imperfect understanding of these galactic foregrounds. And so, the story of dark flow is a beautiful example of the scientific process in action. It is a story of a tantalizing and potentially revolutionary anomaly that has spurred a decade of intense and often contentious debate. It has forced us to refine our observational techniques, to improve our data analysis methods, and to think more deeply and more critically about the fundamental assumptions of our cosmological models, whether dark flow ultimately proves to be a real physical phenomenon, a window into a universe beyond our own, or a beautiful, but ultimately illusory, statistical ghost. The quest to understand it has already enriched and deepened our understanding of the cosmos. It is a reminder that in science, the journey is often as important as the destination, and that the greatest discoveries are often born from the patient and rigorous investigation of the subtle anomalies that do not quite fit our current and always provisional picture of the world. The term dark flow is an evocative one, a name that captures the mysterious and unseen nature of this potential large-scale cosmic motion. It is a phenomenon that, if real, would force us to confront the limits of our own observable universe and to grapple with the possibility of gravitational influences from beyond. The first tantalizing hints of its existence emerged from the careful analysis of the cosmic microwave background radiation, the faint ancient light that fills all of space. The CMB is not perfectly uniform. It has a dipole anisotropy, a pattern where it is slightly hotter in one direction of the sky and slightly colder in the opposite direction. This is a well-understood effect, and it is caused by our own motion through the cosmos. The entire local group of galaxies, including our own Milky Way, is moving at a speed of about 630 kilometers per second relative to the CMB. But when astronomers in 2008 used the CMB to measure the motions of more distant galaxy clusters, they found that these clusters seem to have an additional common velocity component, a bulk flow that was not explained by the gravitational pull of the known, large-scale structures within our observable universe. This unexpected and coherent motion was christened dark flow. The name is a deliberate echo of the other great dark mysteries of modern cosmology, dark matter and dark energy. Dark matter is the invisible, gravitational scaffolding that holds our galaxies together. Dark energy is the mysterious, repulsive force that is driving the accelerated expansion of the universe. Dark flow, if it exists, would be the third member of this enigmatic cosmic triumvirate, a phenomenon that hints at a universe that is even stranger and more mysterious than our already strange and mysterious standard model would suggest. The leading theoretical explanation for dark flow is that it is the gravitational signature of a massive, and as yet unseen, concentration of matter that lies beyond our cosmic horizon. The universe is structured in a cosmic web of vast filaments of galaxies and dark matter, separated by even vaster, empty voids. It is possible that our own observable universe is just a small part of a much larger filament, and that we are being pulled along, like a piece of driftwood in a cosmic river, by the gravitational attraction of a colossal super-attractor that lies downstream, just over the edge of what we can see. This would not require any new physics. It would simply mean that the distribution of matter in the universe is not as uniform on the very largest scales as we have assumed. Another, and more exotic, possibility is that dark flow is a remnant of the pre-inflationary universe. The theory of cosmic inflation posits that our universe underwent a period of hyper-accelerated expansion in its first fleeting moments. But what was the universe like before inflation? If it was a chaotic and highly inhomogeneous place, then it is possible that our own observable patch of the universe still retains a kind of cosmic tilt, a memory of a primordial, large-scale gradient that was present before inflation smoothed everything out. This tilt could manifest today as a preferred direction of motion, a dark flow. This is a highly speculative idea, but it is a tantalizing one, as it would provide us with our first, albeit very indirect, glimpse of the universe as it was before the beginning of the Big Bang as we know it. The observational evidence for dark flow, however, remains controversial and highly debated. The initial measurements, which were based on the kinematic Sunyaev-Zeldovich effect in the WMAP data, are incredibly subtle and difficult to disentangle from other potential sources of noise and systematic error. Subsequent, and more precise, measurements from the Planck satellite have not confirmed the original, strong detection of dark flow and have placed tight constraints on its possible magnitude. Many cosmologists now believe that the original evidence was likely a statistical fluke or the result of an unaccounted-for astrophysical effect. And yet, the idea has not entirely gone away. There are other independent lines of evidence, from the analysis of the peculiar velocities of large samples of galaxies, that have also hinted at the existence of a large-scale bulk flow, a flow that is not always aligned with the direction of the original dark flow detection, but which is still larger than what is expected in the standard lambda CDM model. The story of dark flow is a story that is still being written. It is a story of a scientific mystery that is playing out at the very limits of our observational capabilities. It is a story that is pushing us to develop new, more powerful, and more precise ways of measuring the large-scale motions of the cosmos. And it is a story that is a beautiful and humbling reminder that the universe is not required to conform to our simplest and most elegant theories. It may be a messier, a clumpier, and a more dynamic place than our models would have us believe. And it is in the patient and rigorous investigation of these messy and often contradictory details that the next great breakthroughs in our understanding of the cosmos will likely be found. The discovery of dark flow, if it were to be definitively confirmed, would be a discovery of profound and potentially revolutionary significance. It would be a direct challenge to the cosmological principle, the foundational assumption that the universe, on its largest scales, is homogeneous and isotropic. And it would force us to confront a new, and perhaps even more humbling, picture of our place in the cosmos. The initial observations that sparked the dark flow debate came in the early 2000s from a team of astronomers led by Alexander Kashlinsky, who were studying the data from NASA's Wilkinson Microwave Anisotropy Probe. WMAP was a space mission that was designed to create a detailed, all-sky map of the cosmic microwave background radiation. One of the many things that can be done with such a map is to measure the peculiar velocities of distant galaxy clusters. This is done through a subtle and difficult-to-measure effect known as the kinematic Sunyaev-Zeldovich effect. A galaxy cluster is filled with a hot, ionized gas. As the photons of the CMB pass through this hot gas, they can scatter off of the fast-moving electrons. If the cluster is moving relative to the CMB, this scattering will impart a tiny but measurable Doppler shift to the CMB photons, a tiny hot or cold spot in the direction of the cluster's motion. The KSZ effect is incredibly faint, a signal that is 1,000 times weaker than the primary temperature anisotropies of the CMB, but by stacking the signals from hundreds of different galaxy clusters, Kashlinsky's team claimed to have detected a coherent bulk flow, a dark flow of about 600 to 1,000 kilometers per second, in a specific direction towards the constellations of Centaurus and Vela. This result was met with a great deal of excitement, but also with a great deal of skepticism. The KSZ effect is notoriously difficult to measure, and there are many potential astrophysical and instrumental effects that could mimic such a signal. The debate intensified when subsequent and more precise measurements from the Planck satellite failed to confirm the original strong WMAP detection. The Planck data, which is of a much higher resolution and sensitivity, showed no evidence for a large-scale, coherent flow of the magnitude that had been initially claimed. This led many in the cosmological community to conclude that the original dark flow detection was likely a statistical anomaly or a systematic error. And yet, the story is not quite so simple. There are other, independent methods for measuring large-scale flows, methods that do not rely on the CMB. These peculiar velocity surveys use a variety of techniques to measure the distances to a large number of galaxies, and they then compare these distances with the galaxies' redshifts to infer their motions relative to the smooth Hubble expansion. And a number of these surveys have also found evidence for a large-scale bulk flow, a flow that is larger than what is predicted by the standard lambda CDM model. The direction of this flow is not always consistent with the original dark flow detection, and the statistical significance of these results is still a matter of debate. But the persistence of these anomalies, in different data sets and with different techniques, suggests that there may be something real and as yet unexplained going on in the large-scale dynamics of our local universe. The theoretical implications of a real physical dark flow would be immense. It could be a sign that our observable universe is just a small part of a much larger and more inhomogeneous structure, a structure that is shaped by the gravitational influence of a vast and as yet unseen concentration of mass that lies just beyond our cosmic horizon. This would not necessarily require a revision of the fundamental laws of physics, but it would require a major revision of our understanding of the initial conditions of our universe. It would suggest that the process of cosmic inflation did not, in fact, smooth the universe out as perfectly as we had assumed. Alternatively, dark flow could be a sign of new and more exotic physics. It could be the signature of a long-range and as yet undiscovered force. It could be the result of a collision with another bubble universe in the multiverse. Or it could be a sign that our understanding of gravity itself, as described by Einstein's general relativity, needs to be modified on the very largest cosmological scales. The story of dark flow is a story that is still very much in progress. It is a story that is being played out at the very limits of our observational capabilities. A story that is full of subtle signals, of complex statistical analyses, and of passionate scientific debate. It is a beautiful example of how science works, of how a single, anomalous, and potentially revolutionary observation can spur a decade of new research, new experiments, and new creative theoretical ideas, and it is a story that is a profound and humbling reminder that the universe is not required to conform to our simplest models, and that there are likely still great and beautiful mysteries waiting to be discovered in the vast and largely unexplored territory of the cosmos. To disentangle the faint and potentially revolutionary the signal of dark flow from the complex and noisy tapestry of the cosmos, scientists must employ a sophisticated and multi-pronged observational and analytical approach. The first and most crucial of these is the precise measurement of the cosmic microwave background radiation. The CMB is our ultimate cosmic reference frame. It is the light from the very early universe, and it is, to an incredible degree of precision, isotropic, the same in all directions. Any motion of an object relative to this cosmic rest frame will produce a measurable Doppler shift in the CMB photons. We have already discussed the KSZ effect, the subtle temperature shift that is caused by the motion of a galaxy cluster through the CMB. But there are other, and often more robust, ways to measure these peculiar velocities. Redshift surveys are a powerful and complementary tool. The redshift of a galaxy is a measure of its total velocity away from us. This velocity has two components: the Hubble flow, the velocity due to the overall uniform expansion of the universe, and the peculiar velocity, the galaxy's own personal motion through space, which is caused by the gravitational pull of the local large-scale structures. If we can independently measure the distance to a galaxy using a standard candle like a Cepheid variable or a Type Ia supernova, then we can use Hubble's law to calculate what its velocity should be due to the cosmic expansion. The difference between the observed velocity and the expected Hubble velocity is its peculiar velocity. By patiently and meticulously measuring the distances and the redshifts of thousands, and soon millions of galaxies, we can build up a three-dimensional map of the peculiar velocity field of our local universe. And it is in this map that we can search for the telltale, large-scale, coherent flows that might be the signature of dark flow. The analysis of the distribution of the galaxies themselves is another crucial line of inquiry. The galaxies are not scattered randomly through space. They are organized in a vast, interconnected, cosmic web of filaments, walls, and clusters, separated by giant, empty voids. This web is the visible tracer of the underlying and much more massive scaffolding of dark matter. By creating a detailed, three-dimensional map of this cosmic web, we can build a model of the gravitational field of our local universe. We can then use this model to predict what the peculiar velocities of the galaxies should be, based on the gravitational pull of the known large-scale structures. The comparison of these predicted peculiar velocities with the observed ones is a powerful test of our overall cosmological model. And any significant and large-scale discrepancy between the two, any motion that cannot be explained by the gravity of the stuff we can see, is a potential and deeply exciting signature of dark flow. One of the great observational campaigns that is currently underway to perform this kind of analysis is the Sloan Digital Sky Survey, which has, over the last 2 decades, created the most detailed, three-dimensional map of the universe ever made. And future surveys, like the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope, will expand this map to cover a much larger volume of the universe, and with a much greater precision. To analyze these vast and incredibly complex data sets, scientists must rely on a sophisticated toolkit of statistical methods. They use techniques like principal component analysis and correlation function analysis to search for the subtle and often hidden patterns in the distribution and the motion of the galaxies. And they compare their observational data with the results of large-scale, n-body computer simulations. These are massive and computationally intensive simulations that model the evolution of a large chunk of the universe, starting from the initial conditions that are inferred from the CMB, and including all the known physics of gravity, of dark matter, and of dark energy. By running thousands of these simulations, with slightly different initial conditions and cosmological parameters, we can create a statistical ensemble of possible universes. We can then compare the properties of our own observed universe, the structure of its cosmic web, the magnitude of its bulk flow with this ensemble of simulated universes, to see if our own universe is a typical or a rare outcome of our standard cosmological model. It is in the careful and often painstaking comparison of all these different and complementary lines of evidence, the subtle whispers of the CMB, the precise measurements of the galaxy redshifts and distances, the vast three-dimensional maps of the cosmic web, and the powerful statistical insights of our supercomputer simulations, that the truth about the mysterious and tantalizing phenomenon of dark flow will one day be revealed. The concept of dark flow, with its suggestion of a large-scale, coherent motion of galaxy clusters, is a profound and direct challenge to the standard cosmological picture of a smooth and largely uniform universe. It is a phenomenon that is distinct from, but also deeply and intriguingly connected to, the other great dark mysteries of our cosmos, dark matter and dark energy. Dark matter, as we have seen, is the invisible gravitational scaffolding that dominates the matter content of our universe. It is the cosmic web upon which the luminous, visible galaxies are strung like jewels. The peculiar velocities of galaxies and galaxy clusters are, for the most part, a direct response to the gravitational pull of this underlying dark matter distribution. A galaxy cluster is falling into the gravitational well of a larger supercluster, which is itself being pulled along a vast dark matter filament. Dark flow, if it is a real physical phenomenon, is a motion that is, in addition to this locally induced gravitational motion, it is a large-scale bulk flow that seems to be superimposed on top of the more complex and more chaotic dance of the cosmic web. The question is, what is the source of this extra motion? Is it simply the gravitational pull of an even larger, and as yet unmapped, concentration of dark matter that lies beyond our observable horizon? Or is it a sign of something more exotic? Dark energy is the other great dark mystery. It is the smooth and gravitationally repulsive form of energy that is driving the accelerated expansion of the universe. In the standard cosmological model, dark energy is assumed to be a cosmological constant, a form of energy that is perfectly homogeneous and isotropic, the same everywhere and in all directions. But what if it is not? What if dark energy is not a constant, but is a dynamic and slightly inhomogeneous quintessence field? In this scenario, there could be subtle, large-scale variations in the density of dark energy across the universe. And since dark energy is a source of gravity, these variations could, in principle, create a large-scale gravitational gradient, a kind of cosmic hill that could cause our local patch of the universe to slide in a particular direction. The observed dark flow could be a manifestation of our own local universe surfing on a vast and very gentle wave of dark energy. This is a highly speculative, but a very exciting idea, as it would provide us with our first, albeit very indirect, observational handle on the nature of dark energy itself. The relationship between these three dark phenomena is one of the central and most profound puzzles in all of modern cosmology. Are they three separate and unrelated mysteries, or are they different and perhaps interconnected manifestations of a single, deeper, and as yet unknown dark sector of physics? The story of dark flow is a story that is being played out at the grand and often invisible intersection of these three great cosmic unknowns, and it is a story that is a powerful reminder that the universe we can see, the familiar, luminous world of stars and of galaxies, is just a thin, and perhaps a very misleading, tracer of a much deeper, much darker, and much more mysterious reality. The confirmation of the existence of dark flow would be a discovery of immense and truly paradigm-shifting significance. It would be a moment that would force us to fundamentally reevaluate our understanding of the universe, of our place within it, and of the very limits of our own cosmic knowledge. At its most basic level, a confirmed dark flow would be a direct and powerful refutation of the cosmological principle, the long-held and deeply cherished assumption that the universe, on its largest scales, is homogeneous and isotropic. It would tell us that our universe has a preferred direction, a large-scale anisotropy, a cosmic axis. This would not be a return to a pre-Copernican, Earth-centered cosmos, but it would be a profound and deeply unsettling departure from the modern and almost religiously held principle of cosmic mediocrity. It would suggest that our own local patch of the universe is not a fair sample of the cosmos as a whole, but is part of a much larger and more structured cosmic flow. The implications for our understanding of the origin and the evolution of the universe would be immense. The standard inflationary model predicts a universe that is, on the largest scales, almost perfectly smooth and uniform, a large scale, and statistically significant. Dark flow would be a major challenge to this picture. It would suggest that our current models of inflation are either incomplete or incorrect. It might require a more complex and perhaps a more chaotic inflationary scenario, one that could leave behind a large-scale primordial tilt or gradient in the fabric of space-time. The discovery of dark flow would also have a profound impact on our understanding of the nature of dark matter and dark energy. As we have seen, it could be the first tantalizing clue that these mysterious dark components of our universe are more complex, more dynamic, and more inhomogeneous than our simplest models have assumed. But perhaps the most profound and most existentially challenging implication of dark flow would be its suggestion of a reality that lies beyond our own observable universe. If the flow is being caused by the gravitational pull of a vast and unseen concentration of mass that lies beyond our cosmic horizon, then it would be the first direct and empirical piece of evidence for the existence of a trans-horizon reality. It would be a confirmation that our own observable universe is not the whole story, that it is just a small and gravitationally influenced part of a much grander and largely inaccessible cosmic structure. This would be a discovery of almost unimaginable philosophical significance. It would be a moment that would be comparable in its impact on the human worldview to the discovery by Hubble that our own Milky Way galaxy is just one of many. It would be another great decentering, another profound lesson in our own cosmic smallness. And it would open up a whole new and previously purely speculative realm of scientific inquiry, the study of the ultra-large-scale structure of the cosmos, the physics of the multiverse, the exploration of the realities that lie beyond the edge of our own limited cosmic view. The search for dark flow is a high-stakes and high-risk scientific endeavor. The signal is faint, the analysis is difficult, and the potential for systematic error is large. But the potential, scientific and philosophical, payoff is immense. It is a search that is being conducted at the very limits of our current observational and analytical capabilities. And it is a search that is a beautiful testament to the relentless and often audacious human desire to push those limits, to peer beyond the horizon, and to glimpse the true, and perhaps the unimaginable, scale and structure of our cosmic home. The story of our scientific understanding of the universe is a story that is written in the language of observational evidence. It is a story that is built not on a foundation of pure philosophical speculation, but on the hard and often difficult to obtain currency of empirical data. And it is a story that has been, for the most part, a journey of a constantly expanding and often shockingly widening of our cosmic horizons. The discovery of the cosmic microwave background radiation in 1965 was one of the great and most pivotal of these observational milestones. It was the discovery of the fossilized light from the Big Bang itself, the definitive proof that our universe had a hot, dense, and fiery beginning, and the subsequent and ever more precise mapping of the tiny temperature fluctuations in this ancient light has become the cornerstone of modern precision cosmology, allowing us to measure the age, the composition, and the geometry of our universe with an accuracy of a few percent. The discovery of the redshift of the distant galaxies by Edwin Hubble in the 1920s was another such paradigm-shifting, observational discovery. It was the first direct evidence that our universe is not static, but is a dynamic and expanding entity, and the precise and modern measurements of this cosmic expansion. Using the standard candles of type Ia supernovae have led to the even more profound and deeply mysterious discovery of the accelerating expansion and the existence of dark energy. The discovery of the first exoplanets in the 1990s was another great observational breakthrough. It transformed the ancient and purely philosophical question of the plurality of worlds into a vibrant and data-driven field of modern scientific inquiry. And with the thousands of exoplanets that have now been discovered by missions like Kepler and TESS, we are, for the first time, beginning to get a statistical answer to the question of how common, or how rare, Earth-like, and potentially habitable worlds might be in our galaxy. The first direct detection of gravitational waves in 2015 by the LIGO Observatory was the most recent, and in many ways, the most profound of these great observational revolutions. It has opened up a completely new and non-electromagnetic window onto the cosmos, a window that allows us to hear the violent and previously silent cataclysms of colliding black holes and neutron stars. The story of modern cosmology is a story of these and many other beautiful and powerful observational discoveries. It is a story that is a testament to the power of human ingenuity, to our ability to build ever more powerful and more sensitive instruments to probe the secrets of the cosmos. And it is a story that is far from over, with a new generation of telescopes, of gravitational wave detectors, and of large-scale galaxy surveys. We are poised on the edge of a new era of even more profound and even more surprising observational discoveries that will undoubtedly challenge our current theories and that will open up new and as yet unimagined vistas in our understanding of the universe. The story of the discovery of dark flow is a beautiful case study in the subtle and often contentious art of wringing a profound and potentially revolutionary scientific conclusion from a faint and noisy observational signal. It is a story that began in the early 2000s with a series of papers from a team of astronomers led by Alexander Kashlinsky. And it is a story that is a testament to the power of a new and very difficult observational technique. The measurement of the kinematic Sunyaev-Zeldovich effect, the CMB, as we have seen, is a remarkably uniform thermal bath of photons that fills the entire universe, but it is not perfectly uniform. It has a dipole anisotropy, which is caused by our own motion through the cosmos. And it has a set of much smaller primordial anisotropies, the fossilized remnants of the quantum fluctuations from the very early universe. The KZ effect is a third, and even more subtle, type of anisotropy. It is a secondary anisotropy, one that is created not in the early universe, but more recently, by the interaction of the CMB photons with the hot ionized gas in a moving galaxy cluster. As the CMB photons pass through this gas, a small fraction of them will scatter off of the fast-moving electrons. If the cluster is moving relative to the CMB, the scattering will impart a tiny Doppler shift to the photons, making the CMB appear slightly hotter in the direction of the cluster's motion, and slightly colder in the opposite direction. The effect is incredibly small, on the order of a few microkelvin, and it is very difficult to distinguish from the much larger primordial anisotropies. But by using a clever statistical technique, by stacking the signals from hundreds of different and carefully selected X-ray bright galaxy clusters, Kashlinsky's team claimed to have been able to isolate this faint KSZ signal. And what they found was a surprise. The clusters did not seem to be moving randomly. They seemed to have a common and statistically significant velocity component, a bulk flow of about 600 kilometers per second, in a specific and very puzzling direction. This was the first and most direct evidence for dark flow, but the result was, and remains, highly controversial. Other teams, using different and in some cases more precise data from both the WMAP and the Planck satellites have not been able to reproduce this strong detection. The debate is a complex and a highly technical one. It revolves around the subtle and difficult issues of how to properly subtract the much brighter primordial CMB signal, how to account for the contaminating emission from our own galaxy, and how to properly model the complex gas dynamics within the galaxy clusters themselves. It is a debate that is at the very cutting edge of precision cosmology, and it is a debate that is still, in many ways, unresolved. But the story of dark flow is not just about the KSZ effect. As we have seen, there are other and completely independent ways to measure the large-scale motions of the universe. Using the peculiar velocities of large samples of galaxies and supernovae. And many of these other studies have also found hints of a large-scale bulk flow, a flow that is larger than what is predicted by our standard cosmological model. The directions of these flows are not always consistent with each other, or with the original dark flow detection. And the statistical significance of these results is still a matter of active and often heated debate. But the persistence of these anomalies in different data sets and with different and independent techniques is a tantalizing and deeply intriguing puzzle. It is a puzzle that is a powerful and a beautiful reminder that even in this era of precision cosmology, the universe still has the capacity to surprise us. The cosmic microwave background radiation is more than just a pretty picture. It is the single, most information-rich cosmological data set we have. It is a fossil, a snapshot of the universe when it was just a few 100,000 years old. And it is a document that is written in the subtle and beautiful language of temperature and polarization. The temperature fluctuations in the CMB, the tiny 1 part in 100,000 hot and cold spots, are a direct and almost pristine image of the primordial density fluctuations that were generated during the period of cosmic inflation. The statistical properties of these fluctuations, their overall amplitude, their distribution of sizes, the subtle way in which their amplitude changes with scale have been measured with incredible precision by satellites like WMAP and Planck. And these measurements have allowed us to determine the fundamental cosmological parameters of our universe, its age, its geometry, its composition with an accuracy of a few percent. They are the measurements that have established the standard lambda CDM model of cosmology as our new and remarkably successful paradigm. But the CMB is not just a map of the early universe's density, it is also a map of its velocity. The primordial density fluctuations were not just standing waves, they were also associated with a field of primordial velocities, regions of the primordial plasma that were moving relative to the overall cosmic rest frame. And these primordial velocities have left their own subtle imprint on the CMB. This is the source of the kinematic Sunyaev-Zeldovich effect, the Doppler shift that is induced in the CMB photons as they pass through a moving galaxy cluster. And it is in the careful and incredibly difficult measurement of this effect that the first tantalizing hints of dark flow were found. The CMB is also a powerful backlight that can be used to illuminate the entire intervening history of the universe. As the CMB photons travel to us over 13.8 billion years, their paths are bent and deflected by the gravitational pull of all the matter they pass through, a phenomenon known as weak gravitational lensing. By measuring the subtle statistical distortions in the pattern of the CMB hot and cold spots, we can create a map of the distribution of all the matter, and particularly the dark matter, between us and the surface of last scattering. This is a powerful and completely independent way to probe the large-scale structure of the universe and to test our cosmological model. And the CMB is also polarized. The light of the CMB has a subtle but measurable polarization, which was created by the scattering of the photons off of the electrons in the primordial plasma. The pattern of this polarization contains a wealth of additional cosmological information. And it is in this polarization pattern that one of the great and most sought-after holy grails of modern cosmology may be hidden, the signature of primordial gravitational waves from the period of cosmic inflation. These gravitational waves would have created a unique and very faint B-mode pattern in the CMB polarization. A swirling, vortex-like pattern that cannot be produced by simple density fluctuations. The detection of these primordial B-modes would be a direct and smoking gun confirmation of the theory of cosmic inflation, and it would give us a direct window into the physics of the universe at the incredible and otherwise inaccessible energies of the very first moments of creation. The cosmic microwave background is a gift that keeps on giving. It is a single, static, and seemingly simple image of the infant universe. But it is an image that is so rich, so complex, and so full of information that we will likely be mining its secrets for decades to come. And it is in the ever more precise and ever more subtle analysis of this beautiful, ancient light that the answers to some of the deepest and most profound of all our cosmic questions, the nature of inflation, the origin of structure, and the reality of dark flow, are likely to be found. Galaxy clusters, the largest gravitationally bound objects in the universe, are the great cosmic cities of our cosmos. They are vast and often spectacular. Congregations of hundreds or even thousands of individual galaxies, all orbiting within a common and immensely massive halo of dark matter. And they are not just beautiful astronomical objects, they are also powerful and uniquely valuable cosmological laboratories. They are the most massive and therefore the most biased peaks in the primordial density fluctuation field, and so their number and their spatial distribution are a very sensitive probe of the underlying cosmological parameters. By simply counting the number of galaxy clusters as a function of their mass and their redshift, we can place powerful constraints on the total amount of matter in the universe, on the nature of dark energy, and on the amplitude of the initial density fluctuations. Galaxy clusters are also powerful gravitational lenses. The immense concentration of mass in a cluster, most of which is in the form of dark matter, creates a deep and powerful gravitational well that can significantly bend and distort the light from the more distant background galaxies that lie behind it. This can create a beautiful and scientifically invaluable pattern of distorted arcs and multiple images, a cosmic mirage that can be used to map the distribution of the mass, and particularly the dark matter, in the cluster with incredible precision. This is one of our most direct and most powerful ways of studying the properties of dark matter and of testing our theories of gravity in the strong field regime. The hot, X-ray emitting gas that fills the vast spaces between the galaxies in a cluster is another rich source of cosmological information. The temperature and the density of this gas are a direct measure of the depth of the cluster's gravitational potential well, providing an independent way to measure its total mass. And, as we have seen, the motion of this gas relative to the CMB can be used to measure the cluster's peculiar velocity through the kinematic Sunyaev-Zeldovich effect. This is the very technique that was used in the first tantalizing detection of dark flow. Galaxy clusters are, in a very real sense, the canaries in the cosmic coal mine. They are the largest, and in many ways the simplest, of all the cosmic structures, and so they are often the first place that we can look for the subtle and often unexpected signatures of new, and as yet undiscovered, physics. The study of their motions, of their distribution, of their internal structure is a multifaceted and deeply interdisciplinary endeavor. an endeavor that combines the tools of optical astronomy, of X-ray astronomy, of radio astronomy, of gravitational lensing, and of large-scale computer simulations. And it is an endeavor that is at the very heart of our quest to understand the large-scale structure of our universe, and to search for the faint, and perhaps a very strange, whisper of the mysterious, and deeply compelling phenomenon of dark flow, the large-scale distribution of galaxies in our universe. The cosmic web is one of the most beautiful and most profound structures in all of nature. It is a vast and intricate tapestry of filaments, of walls, and of clusters, all woven from the invisible threads of dark matter, and all separated by vast and largely empty cosmic voids. And it is a structure that is a direct and almost pristine fossil of the tiny quantum fluctuations that were generated in the first fleeting moments of the universe's existence. The story of how this web was formed is the story of a simple and very powerful physical process, gravitational instability. The universe, at the time of the Big Bang, was an almost perfectly smooth and uniform soup of matter and of radiation. But it was not perfectly smooth. It had tiny, 1 part in 100,000 variations in its density, the macroscopic remnants of the primordial quantum fluctuations. And in a universe that is dominated by gravity, these tiny initial inhomogeneities are destined to grow. A region that starts out with a slightly higher than average density will have a slightly stronger than average gravitational pull. It will begin to attract the matter from its surrounding lower density regions. This makes it even denser, which in turn increases its gravitational pull, which in turn attracts even more matter. It is a classic, runaway, rich-get-richer process. Over the billions of years of cosmic history, this simple and relentless process of gravitational collapse has transformed the smooth and almost featureless infant universe into the rich and beautifully structured adult universe that we see today. The initially spherical, overdense regions have collapsed to form the dense and roughly spherical halos of dark matter that are the homes of individual galaxies and galaxy clusters. The initially linear, filamentary overdensities have collapsed to form the vast and often spectacular filaments of the cosmic web, and the initially underdense regions have had their matter drained away, becoming the vast and largely empty cosmic voids. The detailed, statistical properties of this cosmic web, the sizes of the voids, the thickness of the filaments, the mass of the clusters, the way in which they are all interconnected, are a very sensitive probe of the underlying cosmological model. They depend on the total amount of matter in the universe, on the nature of dark matter, on the properties of dark energy, and on the specific statistical properties of the initial primordial fluctuations. By creating vast and ever more precise three-dimensional maps of the distribution of the galaxies with large-scale redshift surveys like the Sloan Digital Sky Survey, we can measure these statistical properties with incredible precision. And by comparing these measurements with the predictions of our theoretical models and of our large-scale computer simulations, we can perform a powerful and very stringent test of our overall cosmological paradigm. The study of the cosmic web is also a crucial tool in the search for dark flow. The gravitational pull of the cosmic web is the primary, and in the Standard Model, the only source of the peculiar velocities of the galaxies. By mapping this web, we can build a model of the local gravitational field, and we can then predict what the motions of the galaxies should be. Any large-scale and statistically significant deviation from this prediction, any flow that cannot be explained by the pull of the visible cosmic web, is a potential and deeply exciting signature of a new and as yet unexplained cosmic phenomenon. The tools of the modern observational cosmologist are a beautiful and powerful testament to the human ability to extend our senses and to probe the deepest and most distant secrets of the universe. At the heart of this toolkit is the telescope. In all its many and wonderfully diverse forms, the great ground-based optical telescopes, with their giant multimeter mirrors and their sophisticated adaptive optics systems that can correct for the blurring effect of the Earth's atmosphere, are our primary tools for creating the vast three-dimensional maps of the cosmic web. The Sloan Digital Sky Survey, with its dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, has been the workhorse of this field for the last 2 decades, and the next generation of survey instruments, like the Dark Energy Spectroscopic Instrument on the 4-meter Mayall Telescope at Kitt Peak, and the Vera C. Rubin Observatory, with its revolutionary 8.4-meter 3-mirror design and its 3.2 gigapixel camera, are set to expand these maps to cover a much larger volume of the universe, and with a much greater depth and precision. The space-based telescopes, like the Hubble Space Telescope and its successor, the James Webb Space Telescope, are our primary tools for peering back in time to the very earliest epochs of galaxy formation. By placing a telescope above the atmosphere, we can achieve a level of sharpness and of sensitivity that is simply not possible from the ground. And by observing in the infrared part of the spectrum, as the Webb telescope does, we can see the highly redshifted light from the most distant, and therefore the earliest of all the cosmic objects. But our view of the universe is not limited to the optical and the infrared. A host of other specialized telescopes allow us to see the cosmos in a completely different and often complementary light. The great radio telescopes, like the Atacama Large Millimeter/Submillimeter Array in the high desert of Chile, can peer into the cold, dark, and dusty molecular clouds where new stars and planets are being born. The X-ray telescopes, like the Chandra X-ray Observatory and the XMM Newton, can see the hot million-degree gas that fills the vast spaces between the galaxies in a cluster, and the matter that is being heated to extreme temperatures as it spirals into a supermassive black hole. And the gravitational wave observatories, like LIGO and Virgo, are our new and revolutionary ears on the cosmos, allowing us to listen to the faint and previously silent tremors in the fabric of space-time itself. To analyze the immense and often overwhelming torrent of data that is flowing back from these diverse and powerful instruments, cosmologists rely on an equally sophisticated and equally powerful set of computational and statistical tools, the large-scale n-body simulations, which can model the evolution of billions and soon trillions of dark matter particles in an expanding universe, are an essential tool for connecting our theoretical models with our observational data, and the new and rapidly evolving techniques of machine learning and artificial intelligence are becoming an indispensable tool for sifting through these vast and complex data sets, for finding the subtle and often hidden patterns, and for making the new and often unexpected discoveries that are driving our field forward. The study of a phenomenon like dark flow is an endeavor that requires the full and a deeply synergistic application of all of these different and wonderfully complementary tools. It is a puzzle that can only be solved by piecing together the subtle clues from a wide range of different and independent lines of evidence. And it is a beautiful example of how modern big data science, in its most ambitious and most profound form, is a deeply collaborative and a truly global human adventure. The theoretical frameworks that we use to understand the origin and the evolution of the universe are some of the most beautiful, most powerful, and most ambitious intellectual constructions in the entire history of science. At the very top of this theoretical pyramid sits Einstein's general theory of relativity, our modern and incredibly successful theory of gravity. It is the theory that provides the dynamical and geometric language for describing the expanding and evolving space-time of our universe. And it is the theory that makes the precise and well-tested predictions for the large-scale phenomena of the cosmic expansion, of gravitational lensing, and of the cosmic microwave background. The second great pillar of our theoretical understanding is the Standard Model of particle physics. This is a quantum field theory that describes the other three fundamental forces of nature and all the known elementary particles. The Standard Model is essential for understanding the physics of the very early and very hot universe, the physics of Big Bang nucleosynthesis, and the physics of the processes that are at play in the hearts of stars and in the most energetic astrophysical phenomena. These two theories, general relativity and the Standard Model, when combined in the framework of the hot Big Bang model, form our standard and remarkably successful model of cosmology. But this Standard Model is, as we have seen, incomplete. It requires the addition of a number of new and as yet unexplained ingredients to match our modern precision observations. It requires a period of cosmic inflation in the very early universe to explain the observed smoothness and flatness of our cosmos. It requires the existence of dark matter to explain the observed motions of galaxies and the formation of the large-scale structure. And it requires the existence of dark energy to explain the observed accelerating expansion of the universe. These three new ingredients in inflation, dark matter, and dark energy are the great, and still largely mysterious, frontiers of modern fundamental physics, and the theoretical frameworks that have been developed to try and explain them, like supersymmetry, or string theory, or quintessence, are the speculative and often beautiful extensions of our standard theoretical picture. The theory of dark flow, if it were to be confirmed, would be another such, and perhaps an even more radical extension. It is a phenomenon that is not predicted by our standard lambda CDM model. And to explain it, we would likely need to invoke a new and as yet unknown theoretical framework. This could be a framework that modifies our understanding of the initial conditions of the universe, that modifies our understanding of the nature of dark energy, or that even, in its most radical form, modifies our understanding of the fundamental laws of gravity themselves. The development and the testing of these new theoretical frameworks is the primary, and often the most exciting, work of the modern theoretical cosmologist. It is a creative and often a deeply intuitive process, a process that involves a delicate and often a very beautiful dance between the rigor of mathematics, the constraints of observation, and the free and often a very wild play of the human imagination. And it is a process that is a testament to the profound, and perhaps the unending, human desire to build a coherent, a beautiful, and a complete intellectual story of our cosmic home. The concept of dark flow, with its tantalizing suggestion of a universe that is being influenced by forces and by structures that lie beyond our own observable horizon, is a concept that is deeply and inextricably linked to the theory of cosmic inflation. Inflation, as we have seen, is the theory that our universe underwent a period of hyper-accelerated, exponential expansion in its first fleeting moments, and one of the most profound and most mind-bending consequences of this theory is the idea of eternal inflation. In this picture, our own observable universe is just a small and causally connected patch of a much larger and eternally inflating meta-universe, and in this vast and endlessly reproducing meta-universe, other bubble universes, like our own, are constantly being formed. It is a vision of a cosmic multiverse, a vast and perhaps an infinite foam of other worlds. And it is in this context of a multiverse that the phenomenon of dark flow can find a new and deeply speculative theoretical home. One of the most intriguing and most dramatic Of these possibilities is that our own bubble universe has, in its distant past, had a close encounter or even a direct collision with another nearby bubble. Such a collision would have been a cataclysmic event, an event that would have left a deep and potentially an observable scar on the very fabric of our space-time. It could have triggered a shock wave that would have propagated through our universe, creating a large-scale and highly anisotropic pattern of density and of temperature fluctuations in the cosmic microwave background. And it could have imparted a large-scale and coherent kick to our local patch of the universe, setting it in motion relative to the overall cosmic rest frame, a motion that we might, today, be observing as dark flow. This is a highly speculative, but a deeply compelling idea. It is a theory that makes a number of specific, and in principle, testable predictions. The search for the telltale circular bruises in the CMB that could be the signature of such a bubble collision is an active and an ongoing area of research. And the measurement of the statistical properties of the large-scale flows in our universe, the search for a specific and theoretically predicted pattern of motion that could be the remnant of such a primordial kick, is another powerful way to test this extraordinary idea. Another, and perhaps a less dramatic, possibility is that the dark flow is not the result of a direct collision, but is simply the result of the long-range gravitational influence of the other bubble universes in our local multiverse neighborhood. If the distribution of these other bubbles is not perfectly uniform, if there is a large and relatively nearby superbubble or a large and relatively empty supervoid in the multiverse landscape, then this could create a subtle but a large-scale gravitational gradient, a tilt in the fabric of the meta-universe that could be pulling our own local bubble in a particular direction. This is an idea that is even more difficult to test, as the effects would be much more subtle, but it is a beautiful and a deeply profound idea. It is an idea that suggests that our universe is not an isolated island reality, but is an open and an interacting member of a much larger and much more complex cosmic community. The relationship between cosmic inflation, the multiverse, and dark flow is a journey into the very deepest and most speculative frontiers of modern theoretical cosmology. It is a journey that is full of beautiful ideas, of complex mathematics, and of a deep and an enduring sense of wonder at the vast and perhaps the infinite creative potential of the cosmos. The question of whether dark flow can be explained by our existing theories of gravity, or whether it requires a new and more radical kind of physics, is one of the central and most exciting questions in the ongoing dark flow debate. At its heart, this is a question about the validity of Einstein's general theory of relativity on the very largest cosmological scales. General relativity is our standard and incredibly successful theory of gravity. It has been tested with exquisite precision in our own solar system, in the timing of binary pulsars, and in the direct detection of gravitational waves. And it is the theoretical foundation upon which our entire standard cosmological model is built. In the context of this standard model, the peculiar velocities of galaxies and galaxy clusters are understood to be a direct and a purely gravitational response to the distribution of matter, and particularly of dark matter in the universe. A dark flow, if it is a real physical phenomenon, and if it is larger than what can be explained by the gravitational pull of the known large-scale structures within our observable universe, would be a direct and a profound challenge to this picture. The first and most conservative explanation is that our maps of the large-scale structure are simply incomplete. Perhaps there is a vast and as yet unmapped concentration of matter, a super-attractor that lies just beyond our current survey limits, and that is responsible for the observed flow. This would be an exciting but not a revolutionary. Discovery. It would not require any new physics, just a better and a more complete map of our cosmic neighborhood. But what if the flow persists, even after we have accounted for all the matter that we can see and that we can infer within our observable horizon? This is where the more radical and more exciting possibilities come into play. One is that our understanding of gravity itself is incomplete. General relativity is a beautiful and a very successful theory, but it is not the only possible theory of gravity. There are a number of modified gravity theories that are designed to behave just like general relativity on the small scales of the solar system, but which can have a different and a more complex behavior on the very largest cosmological scales. Some of these theories, for example, introduce a new, long-range fifth force of nature, a force that could be responsible for both the accelerated expansion of the universe and for the large-scale dark flow of the galaxies. The testing of these modified gravity theories is a major goal of modern cosmological research, and the study of the large-scale flows in the universe is one of our most powerful tools for doing so. Another and even more exotic possibility is that the dark flow is a sign of a fundamental, and as yet unexplained, anisotropy in the universe itself, a preferred direction that is woven into the very fabric of space-time. This would be a profound and a deeply unsettling discovery. It would be a direct violation of the cosmological principle, and it would force us to completely rethink our most basic and most cherished assumptions about the nature of the cosmos. The search for dark flow is a search that is being conducted at the very limits of our current observational and theoretical understanding. It is a search that is pushing us to create better maps of our universe, to perform more precise tests of our theory of gravity, and to think more creatively and more audaciously about the fundamental nature of reality itself. And it is a search that is a beautiful testament to the power of science to constantly question its own most foundational assumptions and to always be open to the possibility of a new and a more profound surprise. The cosmic web, the vast and beautiful filamentary structure of the large-scale universe, is the visible and the gravitational skeleton upon which the entire cosmic drama is played out, and the study of its structure and of its dynamics is the key to understanding a host of fundamental cosmological questions, from the nature of dark matter to the reality of dark flow. The cosmic web is a direct and a stunningly beautiful manifestation of the primordial density fluctuations that were generated during the period of cosmic inflation. The regions that started out with a slightly higher than average density have, over the billions of years of cosmic history, collapsed under the influence of gravity to form the dense and often spectacular galaxy clusters, the great cosmic cities of our universe. The regions that started out with a slightly lower than average density have had their matter drained away, becoming the vast and largely empty cosmic voids, the great cosmic deserts. And the regions that were in between, the vast and sheet-like walls and the long and sinuous filaments, have become the cosmic highways, the channels along which the galaxies and the dark matter are flowing, from the voids to the clusters. The study of the motions of the galaxies within this web is a powerful tool for cosmology. These peculiar velocities are a direct and a very sensitive probe of the underlying gravitational field that is being generated by the distribution of the dark matter. By measuring these velocities and by comparing them with the predictions of our models, we can perform a powerful and a very stringent test of our overall cosmological paradigm. The phenomenon of dark flow is, in its essence, a claim about a specific and a very strange feature of this peculiar velocity field. It is the claim that, on the very largest scales, there is a coherent and a statistically significant bulk flow, a common motion of our entire local patch of the cosmic web, a motion that cannot be explained by the gravitational pull of the known structures within that patch. The implications of such a flow for our understanding of the cosmic web would be profound. It would suggest that the web itself is not a closed and a self-contained system, but is an open and an interacting one. It would suggest that our local cosmic web is just a small part of a much larger, and perhaps an even more complex, hyperweb, a structure whose gravitational influence can reach across the vast and seemingly impassable gulf of our cosmic horizon. The study of the cosmic web is a field that is still in its infancy. We have, in the last few decades, created the first, and still relatively sparse, maps of our local cosmic neighborhood, but with the next generation of large-scale galaxy surveys, we are poised to expand these maps to cover a much larger volume of the universe, and with a much greater and a much more beautiful detail. And in these new and vast cosmic maps, we will be able to search with a new and a much greater precision for the subtle and perhaps the revolutionary signature of the mysterious and the deeply compelling phenomenon of dark flow. The use of large-scale and computer simulations has become an absolutely essential and an incredibly powerful tool in the modern cosmological quest to understand the formation and the evolution of the large-scale structure of the universe, and to test our theories against the complex, and often noisy, data of our observations. A modern cosmological simulation is a monumental computational undertaking. It is a universe in a box, a virtual cosmos that is created and evolved inside a supercomputer. The simulation typically starts with a large and a representative volume of the universe, filled with a vast number of particles which represent the dark matter. The initial conditions for these particles, their positions, and their velocities are carefully chosen to match the statistical properties of the primordial density fluctuations that have been measured in the cosmic microwave background. The computer then, step by step, calculates the gravitational force between every single particle, and it moves the particles according to these forces and according to the overall background expansion of the universe over the course of many of these small but time steps, which can correspond to billions of years of cosmic evolution. The simple and almost featureless initial state of the simulation evolves through the relentless and beautiful process of gravitational instability into a rich and complex cosmic web of filaments, of walls, and of halos, a structure that looks remarkably and beautifully like the one that we observe in our own real universe. These simulations are a powerful tool for testing our theoretical models. We can run simulations with different cosmological parameters, a different amount of dark matter, a different type of dark energy, a different set of initial conditions, and we can then compare the statistical properties of the resulting virtual universes with the properties of our own. This is a powerful way to constrain our cosmological model, to find the specific and the unique set of parameters that best describes our own cosmic reality. In the context of dark flow, these simulations are a particularly crucial tool. They allow us to ask and to answer a very precise and a very important question in a standard lambda CDM universe. With the initial conditions that have been measured by the Planck satellite, how likely is it that we would observe a large scale of bulk flow of the magnitude that has been claimed by the dark flow proponents? The simulations allow us to create a large and a statistically robust ensemble of possible lambda CDM universes. We can then measure the bulk flow in each of these simulated universes, and we can build up a probability distribution, a cosmic variance, for this quantity. This is the baseline against which we must compare our own, single, and necessarily noisy observation of our own, real universe, the current and still somewhat contentious state of this comparison is that the observed bulk flows in some of the peculiar velocity surveys do seem to be a bit larger than what is typically found in the simulations. The discrepancy is not, as yet, at the level of a 5 sigma discovery, but it is a tantalizing and a deeply intriguing tension, a hint that there may be something missing or something wrong with our standard and otherwise remarkably successful cosmological model. The future of this field lies in the development of even larger and more sophisticated simulations that can model not just the dark matter, but also the complex and often messy physics of the baryonic, normal matter, the gas, the stars, the feedback from supernovae and from active galactic nuclei. And it lies in the close and deeply synergistic collaboration between the theorists who are building these virtual universes and the observers who are mapping our real one. It is in this rich and beautiful dialogue between the simulated and the observed that the next great breakthroughs in our understanding of the cosmos will undoubtedly be found. The story of modern cosmology, from the discovery of the expanding universe to the mapping of the cosmic microwave background, is a story that has had a profound and often a very humbling impact on our understanding of our own place in the cosmos. It is a story that has taken us on a long and often a very dizzying journey of decentering. We are not at the center of the solar system. We are not at the center of the galaxy. Our galaxy is not at the center of the universe, and our universe itself may not have a center. We live in a universe that is, on its largest scales, and to a very good approximation, homogeneous and isotropic. A universe that has no special or privileged position. This is the cosmological principle, and it is the modern and the most profound expression of the Copernican idea of our own cosmic mediocrity. But this is not the end of the story. The discoveries of the last few decades have added a new, and in some ways, an even more profound, set of decenterings to our cosmic story. We have discovered that the very matter we are made of, the baryonic matter of the atoms and the stars, is a tiny and an almost insignificant 5% minority in the cosmic energy budget. The vast majority of the universe is made of dark matter and dark energy, mysterious and invisible, substances whose nature we do not yet understand. We are not just in an ordinary place, we are made of the wrong stuff. And we have discovered that our entire observable universe may just be a tiny, and perhaps an insignificant, bubble in a much larger, and perhaps an eternally inflating multiverse. Our entire cosmic reality may just be one of a vast and perhaps an infinite number of other parallel realities. The phenomenon of dark flow, if it were to be confirmed, would be another, and a very strange twist in this long and often unsettling story of cosmic decentering. It would tell us that our universe is not, in fact, perfectly isotropic. It has a preferred direction, a cosmic axis, a large scale, and as yet unexplained, flow. This would not be a return to a pre-Copernican center of the universe worldview, but it would be a profound and a deeply unsettling departure from the simple and in many ways the comforting idea of a perfectly uniform and perfectly mediocre cosmos. It would suggest that our own local patch of the universe is, in some deep and as yet unexplained way, special. Not special in the sense of being at the center, but special in the sense of being a part of a much larger and more structured cosmic river. The philosophical implications of this are immense. It forces us to confront the very limits of our scientific knowledge and to grapple with the possibility that our universe is a far more complex, a far more structured, and a far more mysterious place than our simplest and most elegant theories would have us believe. It is a journey that is, in many ways, a journey back to a more ancient and perhaps a more humble way of seeing the world, a way that is less focused on the search for a single, simple, and universal law, and is more open to the possibility of a universe that is full of diversity, of complexity, and of a deep and an enduring mystery. The story of Dark Flow, with its tantalizing hints of a reality that lies beyond our own observable horizon, is a story that is deeply and inextricably linked to the primordial and still largely mysterious conditions of the very early universe. The large-scale structure that we see today, the galaxies, the clusters, the cosmic web, is a direct and a gravitationally amplified fossil of the tiny density fluctuations that were present in the universe when it was just a few 100,000 years old. The fluctuations that we see imprinted on the cosmic microwave background, and these primordial fluctuations are, in turn, thought to be the macroscopic remnants of the microscopic quantum fluctuations that were generated during the period of cosmic inflation, in the very first, fleeting moments of the universe's existence, in the standard, simplest model of inflation. These primordial quantum fluctuations are assumed to be Gaussian and isotropic. Gaussian means that their statistical properties are very simple and are completely described by their power spectrum, the amount of fluctuation at each different spatial scale. Isotropic means that these statistical properties are the same in all directions on the sky. The standard, single-field, slow-roll model of inflation makes a very specific and a very successful prediction for these properties, a prediction that has been confirmed with stunning precision by the Planck satellite. But what if the process of inflation was more complex? What if it involved multiple interacting inflaton fields? What if the geometry of the early universe was not perfectly simple and uniform in these more complex and more chaotic inflationary scenarios? It is possible that the primordial fluctuations were not perfectly Gaussian or not perfectly isotropic. There could have been subtle, non-Gaussian correlations between the fluctuations at different scales, and there could have been a subtle statistical anisotropy, a preferred direction in the sky along which the fluctuations were slightly stronger or weaker. And these primordial non-Gaussianities and anisotropies, if they existed, would have been imprinted on the cosmic microwave background. And they would have also seeded a set of large-scale and highly non-trivial primordial velocities in the early universe. The dark flow, if it is a real physical phenomenon, could be a direct and a very powerful observational signature of this kind of more complex and more interesting early universe physics. It could be the fossilized remnant of a large-scale primordial velocity field that was generated by a non-standard inflationary process. The search for these subtle and as yet undetected signatures of non-Gaussianity and of anisotropy in the cosmic microwave background is one of the great and most exciting frontiers of modern observational cosmology. And it is a search that is deeply and inextricably linked to the search for the reality and the origin of the mysterious and the deeply compelling phenomenon of dark flow. The ultimate fate of our universe, the final chapter in the long and beautiful cosmic story, is a question that is deeply and inextricably linked to the nature of the dark energy that is driving its current, accelerated expansion, and the phenomenon of dark flow. If it is a real and a physically significant effect, could provide us with a new and a very powerful clue in our quest to understand this ultimate cosmic mystery. In the standard cosmological model, where dark energy is a simple and a constant, cosmological constant. The future of the universe is a relatively simple, if a somewhat bleak, one. It is a future of eternal and ever-accelerating expansion, a big freeze or a heat death, a future where the galaxies will recede from each other into an eternal, cold, and lonely darkness. But if dark energy is not a constant, if it is a dynamic and an evolving quintessence field, then the future can be much more complex and much more interesting. And the existence of a large-scale dark flow could be a tantalizing hint that this is, in fact, the case. As we have seen, a dark flow could be the result of a large-scale and very gentle gradient in the density of the quintessence field. This would mean that dark energy is not perfectly smooth and uniform, but has a large-scale structure of its own. And if it has a structure, it is likely to be dynamic, to be evolving. This would open up a whole new and a much richer set of possibilities for the future of our universe. If the energy density of the quintessence field is currently decreasing, then the cosmic acceleration could one day slow down, and perhaps even reverse, leading to a future big crunch. If, on the other hand, the energy density of the quintessence field is increasing, a scenario known as phantom energy, then the future could be even more dramatic, a big rip. A future where the ever-increasing repulsive force of the dark energy will eventually become so strong that it will tear apart all the bound structures in the universe, from the galaxy clusters to the galaxies, to the stars, to the planets, and eventually to the very atoms themselves. The study of dark flow, then, is not just a study of the present-day, large-scale motions of our universe. It is also, in a very real and a very profound sense, a study of our cosmic destiny. The faint and subtle, coherent motion of a distant galaxy cluster could be the first and the most important clue that will allow us to distinguish between these different and dramatically divergent cosmic futures. It is a clue that could tell us whether our universe is destined for a long, slow, and quiet fade into an eternal darkness, or for a much more violent, a much more dramatic, and a much more spectacular final act. The search for dark flow and the broader scientific quest to understand the large-scale structure and the dynamics of our universe is a journey that is being played out at the very frontiers of our technological capabilities. It is a journey that is being enabled by a new and a revolutionary generation of telescopes, of surveys, and of computational tools. And it is a journey that is poised to enter a new, and even more exciting, era of discovery in the coming years and decades. The Vera C. Rubin Observatory, which is currently under construction on a mountaintop in Chile, is set to revolutionize the field of time-domain cosmology. With its giant 8.4-meter mirror and its 3.2 gigapixel camera, it will survey the entire southern sky every few nights for a decade, creating a deep and a dynamic movie of the evolving universe. Its vast and exquisitely calibrated dataset of billions of galaxies and supernovae will allow us to measure the peculiar velocities and to map the large-scale flows out of the cosmos with a precision and a statistical power that is far beyond anything we can achieve today. The Euclid Space Telescope, a mission of the European Space Agency, will provide a complementary and a very powerful view. It will create a high-resolution map of the shapes of billions of galaxies, allowing us to measure the subtle, weak gravitational lensing distortions that are caused by the intervening large-scale structure. This will provide us with a direct and a very precise map of the distribution of the dark matter, a map that can then be used to predict the gravitational peculiar velocity field and to search for the anomalous and deeply exciting signature of dark flow. And the Square Kilometer Array, the next-generation global radio telescope, will provide yet another and a very powerful window onto the large-scale universe. It will map the distribution of the neutral hydrogen gas in the early universe, providing a three-dimensional picture of the cosmic web at a time when the universe was just a fraction of its current age. The study of the large-scale flows in this primordial cosmic web will be a powerful and a completely independent test of the dark flow hypothesis. And on the theoretical front, the development of even larger and more sophisticated cosmological simulations that are powered by the next generation of exascale supercomputers will allow us to create virtual universes of unprecedented size and of unprecedented realism. These will be the theoretical laboratories in which we can test our most ambitious and our most creative ideas about the nature of dark matter, of dark energy, and of the mysterious and the deeply compelling phenomenon of dark flow. The future of this field is a future of a deep and a wonderfully synergistic interplay between these revolutionary new observational facilities and these powerful new computational tools. It is a future that promises to be full of new discoveries, of new surprises, and of a new and a much deeper understanding of our beautiful, our mysterious, and our wonderfully dynamic cosmic home. The story of dark flow, with its tantalizing hints of a universe that is larger, more structured, and more mysterious than our standard models would suggest, is a story that is, in many ways, a microcosm of the larger human story of scientific discovery itself. It is a story that begins with a faint and an anomalous signal, a subtle and a difficult-to-measure observation that does not quite fit our pre-existing expectations. It is a story that then proceeds through a long and often a very contentious period of debate, of new observations, of more sophisticated analyses, of the careful and often the painstaking process of ruling out all the possible and more mundane alternative explanations. And it is a story that will, one day, hopefully, culminate in one of two possible outcomes. Either the anomaly will be shown to be a statistical fluke, a systematic error, a beautiful, but ultimately an illusory ghost in the machine. Or it will be confirmed as a real and a physically significant phenomenon, a true and a revolutionary discovery that will force us to abandon our old and our cherished models and to embrace a new, a deeper, and a more profound understanding of the world. This is the way that science, at its best, makes progress. It is not a straight and a triumphant march towards a final and an absolute truth. It is a messy, a human, and a deeply beautiful process, a process of grappling with uncertainty, of living with ambiguity, and of always and forever being open to the possibility of a new and a more wonderful surprise. And the story of dark flow is a powerful and a deeply humbling reminder that even in this modern and seemingly mature era of precision cosmology, the universe still has the capacity to surprise us. It is a reminder that there are still great and beautiful mysteries waiting to be discovered. Mysteries that are hidden in the faint and the subtle. Whispers of the cosmos. Mysteries that are waiting patiently for a new generation of explorers, of thinkers, and of dreamers to come along and to listen. And it is a reminder that the quest to understand our universe and our own small and precious place within it is a journey that is not just about finding the answers, but is also, and perhaps even more importantly, about learning to live with and to be enriched by the deep, the beautiful, and the enduring questions. Imagine something so huge, so powerful, and so intense that it makes our sun look like a tiny, flickering spark. Now, picture this monstrous star burning with a fury so great that it could blast entire solar systems apart with its mere breath. This is not a flight of science fiction. It is real. Somewhere, far out in the vast, star-dusted darkness of the cosmos. Astronomers have found the biggest and most terrifying star ever discovered. Its size, its heat, its raw, untamed energy are beyond anything we can truly and viscerally comprehend. When we look up at the serene beauty of the night sky, we see a tranquil scattering of tiny, twinkling dots. They seem so small, so peaceful, just delicate pinpricks of light against the velvet black. But this is a profound illusion, a deception born of immense distance. Those little lights are, in fact, gigantic, blazing balls of fire. They are cosmic furnaces of unimaginable violence. Deep within their cores, powerful nuclear reactions are constantly and ferociously taking place, fusing the very atoms of the universe and releasing a torrent of energy that lights up entire galaxies, that creates the conditions for planets like our own to exist, and that is so immense that its gravity can bend the very fabric of space and time itself. But not all stars are created equal. Some, like our own sun, are relatively calm and steady. Cosmic home fires that have been shining peacefully for billions of years and will continue to do so for billions more. Others, however, are of a completely different order. They are the true giants of the universe, behemoths of such monstrous proportions that they defy our everyday sense of scale. These enormous stars shine with a brilliance so fierce that they could easily swallow entire planets and still hunger for more. They are not just bright, they are terrifyingly and beautifully powerful. So, what exactly is a giant, say, in the precise language of astronomy? The word giant is not just a casual descriptor of size. It refers to a specific and often dramatic stage in a star's life. After a star has exhausted the primary hydrogen fuel in its core, the fuel it has been patiently burning for millions or billions of years, it undergoes a profound transformation. It begins to fuse heavier elements, like helium, in a shell that surrounds its now inert core. This new, more intense form of fusion creates a powerful, outward pressure that pushes the star's outer layers far out into space. The star begins to swell, to bloat, growing hundreds or even thousands of times larger than it was in its youth. This is the red giant phase, and it is a glimpse into the future of our own sun. But for stars that are born with a much greater mass than our sun, this process is even more extreme. These stellar titans do not just become red giants, they become red supergiants. And in the rarest, most extreme cases, hypergiants, colossal, celestial beasts of such unimaginable size that they could engulf entire solar systems. But how do scientists, from their distant vantage point on a small, rocky planet, even begin to measure something so unbelievably huge? They use units of measurement that are themselves almost beyond our comprehension. Our own sun, for example, has a radius of about 696,000 kilometers. It is a number so large it is difficult to visualize. But now, consider Betelgeuse, the famous red supergiant that marks the shoulder of the constellation Orion. Its radius can be up to 900 times larger than that of our sun. If you were to place Betelgeuse at the center of our solar system, its roiling, fiery surface would stretch far beyond the orbit of Mars, swallowing Mercury, Venus, and Earth in the process. And yet, even Betelgeuse is not the biggest. There is another star, a red supergiant named WOH G64, that dwarfs it. This colossal star, a true cosmic leviathan, may have a radius up to 1,700 times that of our sun. That would make it large enough to stretch beyond the orbit of Jupiter if it sat at the center of our solar system. Imagine a single, blazing star, engulfing half of our planetary family. That is the scale we are talking about. But a star's terrifying size is not its only frightening trait. There is also its brightness, its luminosity, the total amount of energy it radiates into space every second. Our sun produces just the right amount of energy to warm our planet and to nurture the delicate chemistry of life. It is a steady, reliable, and life-giving star. But the largest stars are of a different, more violent temperament. They produce hundreds of thousands, or even millions, of times more light and heat than our sun. They burn through their immense reserves of nuclear fuel at a furious, unsustainable pace, shining with an incredible, almost desperate brilliance, but only for a short time. And when they die, they do not fade away quietly. They go out in a blaze of glory in a spectacular and universe-shaking explosion. Many of these monster stars are found in strange and exotic places in the wild, untamed frontiers of the cosmos. They are often found in faraway satellite galaxies, like the large Magellanic Cloud, a small, irregular galaxy that orbits our own Milky Way. These smaller galaxies often have a different chemical makeup than our own, with lower amounts of the heavy elements like carbon, oxygen, and iron, that astronomers collectively refer to as metals. This low metallicity environment makes it easier for the primordial clouds of gas and dust to collapse and form truly massive stars. These metal-poor galaxies are like cosmic nurseries for the extreme, for the giants, for the stars that push the very limits of what is physically possible. But in space, as in life, being big comes with a heavy price. The bigger a star is, the faster it lives, and the shorter its life. Its immense gravity crushes its core, forcing it to burn its fuel at an incredible rate. A star like our sun can live for a stately 10 billion years. But the biggest, most massive stars are lucky to survive for a few million years, a mere blink of an eye in cosmic time. These are not the gentle, ancient gods of the cosmos, watching over the universe with a patient, steady gaze. They are the fierce, blazing titans, the beautiful and terrifying giants of the night, living fast, dying young, and leaving a spectacular, and often beautiful, corpse in the deep, silent darkness of space. In the far and often unexplored corners of the cosmos, beyond the familiar, graceful swirl of our own Milky Way, lie galaxies so strange and so wild that they seem to break the very rules of how stars are supposed to form. These are not the quiet, orderly, and well-behaved galactic cities that we are used to. They are chaotic, raw, and bursting with a primal, creative energy. And they are the perfect homes for the true monsters of the universe. Some of the brightest and biggest stars ever discovered, colossal behemoths like Stephenson 218 and WOH Scuti, were born in these bizarre galactic neighborhoods, far from the calm and gentle lanes of our own suburban spiral arm. These massive stars do not just pop into existence out of nowhere. They are the product of extreme and often rare cosmic environments, places that act like celestial pressure cookers, forging stars of almost unimaginable size and power. Many of these stellar giants are found in small satellite galaxies or in the dense, crowded hearts of galactic groups, places with a strange and often primordial chemical makeup, places where furious, galaxy-wide waves of starbirth, known as starbursts, are constantly and violently churning up the vast interstellar clouds of gas and dust. To truly grasp how these terrifyingly powerful stars are born, we must first understand the unique and often violent conditions that give rise to them. One of the key ingredients in the recipe for a giant star is something called metallicity. In the precise and sometimes counterintuitive, language of astronomy. Metallicity refers to the abundance of any element that is heavier than hydrogen and helium. These heavier elements, which astronomers collectively call metals, include familiar substances like carbon, oxygen, and iron, all of which were forged in the fiery hearts of previous generations of stars and then scattered into space when those stars died. And here is the surprising and deeply important part of the story: the less of these metals a primordial gas cloud has, the easier it is for that cloud to collapse and form a single, truly massive star. This is because these heavy elements act as a very efficient cooling agent. They are able to absorb the heat from a collapsing gas cloud and then radiate it away into space. This cooling allows the cloud to fragment into many smaller and denser clumps, each of which will then go on to form a relatively small star, like our Sun, but in places with a lower metallicity, like the small satellite galaxies that orbit our own. The gas clouds are less efficient at cooling. They stay warmer, and they are less likely to fragment. Instead of shattering into 1,000 smaller pieces, the entire vast cloud can collapse under its own immense gravity into just one or a few very massive protostars. These metal-poor galaxies become cosmic star factories of a very different kind. They are not mass-producing the small, gentle, and long-lived stars that are common in our own galaxy. They are specializing in the creation of the rare, the extreme, the giants, the blazing titans of the cosmos. In these dense and chaotic stellar nurseries, a process of cosmic Darwinian competition takes hold. The first protostars to form, especially those in the densest, most gas-rich parts of the cloud, get a head start. Their growing gravity allows them to pull in more and more material from their surroundings, effectively starving their smaller, less fortunate neighbors. They grow fast and they grow large, devouring the primordial gas in a kind of cosmic cannibalism, a process where only the gravitationally strongest survive and thrive. But it is not just the initial conditions of the gas cloud that matter. It is also its dynamics. If the cloud is turbulent, if it is full of wild, chaotic motion, or if it is spinning at just the right speed, it can create a gravitational funnel, a process that can efficiently channel a vast amount of material towards the center, feeding the growing protostar with stunning speed. When this happens, when gravity wins a decisive victory over the outward push of gas pressure, a single star can grow to be dozens or even hundreds of times more massive than our Sun, even before its nuclear furnace has fully ignited. And there is a strange and beautiful cosmic irony in all of this. While it is harder to form these enormous stars, once they do exist, they completely dominate their environment. Their intense, powerful light and their ferocious stellar winds can reshape the entire star-forming region around them. Sometimes, the shock waves from their powerful winds can compress the surrounding gas clouds, triggering the birth of a new generation of smaller stars. Other times, their energy is so immense, their radiation so fierce, that they can completely halt any further star formation in their vicinity, effectively sterilizing their own cosmic cradle. It is as if a cosmic queen has been born, a queen who demands all the attention, and who refuses to let anyone else share her brilliant and dazzling spotlight. And here is one of the most fascinating things that scientists have discovered. It was likely much easier for these colossal, monster stars to form in the very early days of the universe. Back then, in the first few 100 million years after the Big Bang, the universe was a much simpler and much purer place. The first galaxies were filled almost exclusively with the pristine, primordial hydrogen and helium that had been forged in the Big Bang itself. There were no metals at all. This was the perfect and perhaps the only time for the formation of what astronomers call population 3 stars. The true first generation of stars to have ever existed. These ancient, primordial giants, born in a metal-free universe, could have grown to be hundreds or even thousands of times more massive than our Sun. We have never seen one of these population 3 stars directly. Their immense mass meant that they lived incredibly fast and died incredibly young. They're spectacular and universe-shaping, lives ending long, long ago. But the massive behemoth stars that we do see today, shining in the distant, metal-poor corners of the cosmos, may be their direct descendants, their modern-day echoes, a faint and beautiful reminder of a time when the universe was younger, wilder, and far more prone to creating monsters. One of the best and most convenient cosmic laboratories for studying this kind of extreme starbirth is a small, irregular, and beautiful satellite galaxy that is our own. Celestial next-door neighbor, the Large Magellanic Cloud, or LMC. If the Milky Way is the vast, sprawling, and relatively orderly capital city of our local galactic neighborhood, then the LMC is the wild, untamed frontier, a rough, energetic, and often surprising place, full of cosmic wonders and dangers. The LMC is a dwarf galaxy, with only about 1/10 the mass of the Milky Way, and it is in a close and often violent gravitational embrace with our own, much larger galaxy. It is located about 163,000 light-years from Earth, and it orbits our galactic center like a loyal, if somewhat chaotic, companion. But despite its small size, the LMC packs a powerful, star-forming punch. In fact, for its size, it is incredibly and unusually prolific. It creates more high-mass stars per unit of gas than our own Milky Way does. The LMC is like a celestial forge, a place that is constantly and furiously hammering out new, brilliant, and often massive stars. Its sky is aglow with fiery, star-forming nurseries and vast, brightly lit clouds of ionized gas, known as nebulae. One of the most famous and most spectacular of these is a region called 30 Doradus, more commonly known as the Tarantula Nebula. It is a vast, sprawling complex of gas and dust, a cosmic spider's web of stellar creation, and it is one of the most active and most luminous star-forming regions in our entire local group of galaxies. So, what makes the LMC so special? It all comes down to a combination of chemistry and chaos. The gas in the LMC has a lower metallicity than the gas in the Milky Way. This means it is less efficient at cooling, and therefore less likely to fragment into a large number of small stars. The LMC does not go for balance and moderation. It goes for the extreme. It makes fewer stars, but the ones it does make are, on average, much larger and more massive. This makes it the perfect birthplace for the true giants of the cosmos, for the stellar behemoths that push the very limits of what is possible. One such behemoth, a star named WOH G64, is hidden deep within the dusty confines of the LMC. It is a red supergiant of almost unimaginable proportions. It is over 1,500 times wider than our Sun, and it shines with a light that is 280,000 times brighter. And it is not just big, it is also in the process of slowly and beautifully falling apart. The behemoth star is shedding its outer layers in a steady, glowing breath, a powerful stellar wind that is enriching the surrounding interstellar medium with the heavy elements that have been forged in its deep, fiery heart. Because it is so relatively close, and because there is less obscuring dust in the line of sight between us and the LMC, it has become an invaluable cosmic laboratory. Telescopes like the Hubble Space Telescope and the Very Large Telescope in Chile can peer directly into its star clusters and its nebulae, and they can watch, in almost real time, as the cosmic drama of stellar life unfolds as the giants are born, as they live out their short and furious lives, and as they finally and spectacularly collapse into the silence of a black hole or a neutron star. And what makes this story even more fascinating is the idea that the Milky Way itself may be the ultimate cause of all this chaos. The immense gravitational pull of our own galaxy is constantly tugging and stretching the LMC, creating powerful tidal forces that stir up and compress its gas clouds, sparking ever more furious waves of star formation. And some scientists believe that billions of years from now, this long and often violent cosmic dance will reach its final spectacular climax. The two galaxies will collide and merge in a galaxy-wide display of celestial fireworks, with stars and gas clouds being flung out into space like glowing, beautiful sparks. The Large Magellanic Cloud is more than just a small satellite galaxy. It is a window into the past, a glimpse of what our own and other galaxies may have looked like in their younger, wilder, and more creative days. Its strange, lopsided structure, its metal-poor gas, its furious, star-forming nurseries. All of these are a reflection of a time when the universe was a more chaotic, more energetic, and more fertile place. And so, when we study the monster stars that are born within it, we are not just learning about the life and death of a single cosmic giant. We are peeking into the ancient and often violent drama that has shaped the very fabric of the cosmos itself. The Large Magellanic Cloud is not just our galactic next-door neighbor. It is a primordial furnace, a wild, beautiful, and powerful reminder that in the grand cosmic story, size isn't everything, but the extremes, the outliers, the monsters, they can often make all the difference. A hypergiant star is a member of the most exclusive and most extreme club in the entire stellar zoo. These are the true heavyweight champions of the cosmos, stars of such immense size, such incredible brightness, and such profound instability that they seem to defy the very laws of physics. They shine with a brilliance that can be millions of times greater than our own sun. And they are constantly shedding their outer layers in powerful, ferocious stellar winds. Streams of hot gas that are blown away by the sheer, overwhelming force of their own internal radiation. In the formal, and often complex, language that astronomers use to classify stars, the Morgan-Keenan, or MK system. A hypergiant is assigned to the very highest luminosity class, a special, and rarely used, category known as Class 0, but you will not often see this label in the scientific literature. It is a term that is reserved for the true, unambiguous monsters, for the stars that are not just big, but are also exhibiting clear and often dramatic signs of extreme instability. More commonly, hypergiants are described with the labels IA0 or IA+, while even the most massive and luminous red supergiants are not usually given this special designation. So, why are astronomers so captivated by these rare and often cantankerous stellar beasts? Because they are the key to understanding some of the most fundamental processes in the universe. How the most massive stars are born, how they live their short and violent lives, and how they ultimately and spectacularly die, often in the titanic and universe-shaping explosions that we call supernovae. Famous examples of hypergiants include the Pistol Star, a brilliant, blue hypergiant that is hidden in the dense, dusty heart of our own galaxy's center. It is one of the most luminous stars ever discovered, shining with the light of several million suns. There is Rho Cassiopeiae, a yellow hypergiant that is so bright it is one of the few hypergiants that is visible to the naked eye from Earth. And there is Mu Cephei, also known as Herschel's Garnet Star, a colossal red hypergiant that is one of the largest and most luminous stars known in our galaxy. The term hypergiant was first coined, in its earlier form of supergiant, in 1956 by the astronomers Feast and Thackeray, to describe a small class of stars that were anomalously and inexplicably bright. Later, in 1971, the astronomer Keenan proposed a more precise, spectroscopic definition. He suggested that the term hypergiant should be reserved for those supergiants that show a very broad and bright emission line in a specific part of their light spectrum, the H-alpha line, which is a specific red wavelength of light emitted by hydrogen. This broad emission line is a telltale sign of a very extended and often unstable atmosphere, and of a star that is losing a tremendous amount of mass through a powerful stellar wind. Today, Keenan's rule is still the one that most scientists use, and it leads to a sometimes confusing situation where a particularly large and stable red supergiant might actually be more luminous, in terms of its total energy output, than a smaller but more unstable and wind-driven star that is officially classified as a hypergiant. One of the key diagnostics that astronomers use to identify a hypergiant is the detailed shape of its spectral lines. In a hypergiant, these lines are often distorted in a characteristic way, a shape known as a P Cygni profile. This profile has a strong emission peak and a blue-shifted absorption trough, and it is the classic signature of a star that is surrounded by a dense, rapidly expanding shell of gas, a direct and unambiguous sign of extreme mass loss. But when it comes to the coolest hypergiants, the red and the yellow ones, this spectroscopic method is not as reliable. And so, for these stars, astronomers must rely on a combination of their immense luminosity and their directly measured, and often staggering, rates of mass loss. Stars that are born with more than about 25 times the mass of our Sun have a very different, and much more dramatic, life story than their smaller, more sedate cousins. They do not spend a long and peaceful life on the main sequence, the stable, hydrogen-burning phase of a star's life. Instead, they quickly evolve into brilliant, blue supergiants, shining with an intense and often unstable light. Then, as they age, they can go through a series of complex and often chaotic transformations. They can expand and cool to become red supergiants, and then contract and heat up again, sometimes oscillating back and forth between hot and cool phases in what astronomers call blue loops. Eventually, they will either explode as a spectacular supernova, or, if they are massive enough, they will shed their entire hydrogen-rich outer envelope and become a very special and very hot kind of star, known as a Wolf-Rayet star, the exposed burning core of a once mighty giant. But for the very most massive stars, those with more than about 40 times the mass of the Sun, the journey is even more direct and even more violent. These stars are so luminous, so powerful, that they can never become a stable red supergiant. The outward pressure of their own internal radiation is so intense that their outer layers are simply blown away before the star ever has a chance to cool down and expand. These are the stars that are destined to become hypergiants. Hypergiants live at the very top of the Hertzsprung-Russell diagram, the grand organizing chart of the stellar kingdom. They are the true cosmic royalty, occupying a region of extreme luminosity and a wide range of temperatures. They can be either young, freshly evolved, and still hydrogen-rich massive stars that have just left the main sequence, or they can be older, more evolved, and hydrogen-poor stars that have already passed through a red supergiant phase and have lost a significant fraction of their initial mass. Just looking at a star's position on the HR diagram is not always enough to tell the difference, but the older, more evolved stars are generally more unstable. Their atmospheres are puffed up, their surface gravity is weaker, and they are constantly teetering on the brink of a delicate and often violated balance point known as the Eddington limit. This is the critical point where the outward push of radiation pressure from inside the star becomes equal to the inward pull of its own gravity. A star that is shining at the Eddington limit is, in a very real sense, on the verge of blowing itself apart. And this is the realm where the hypergiants live. The yellow hypergiants, in particular, are thought to be post-red supergiant stars, stars that have already shed a significant portion of their hydrogen envelopes. The blue hypergiants, on the other hand, can be either pre- or post-red supergiant, their immense luminosity making them inherently unstable regardless of their evolutionary state. And most hypergiants do not shine with a steady light. Their brightness is constantly, and often chaotically, changing. They flicker, they pulse, they have sudden, violent eruptions. In the case of a special class of hypergiants, the luminous blue variables, or LBVs, these eruptions can be so powerful that the star can temporarily increase its brightness by a factor of hundreds or even thousands, becoming one of the most luminous objects in its entire galaxy, before it settles back down into a quieter, though still deeply unstable, state. Hypergiants are rare. They are ephemeral, and they are profoundly and beautifully violent. They are the fleeting and spectacular death throes of the most massive stars in the universe, a final, brilliant blaze of glory before they finally and inevitably collapse into the silence of a supernova and the darkness of a black hole. Hypergiants are not just huge, they shine with an almost unbelievable and often self-destructive brightness. As a star's mass increases, its luminosity does not just increase linearly, it increases dramatically, roughly as the mass to the power of 3.5. This means that a star that is 10 times more massive than our Sun is not just 10 times brighter. It is about 3,000 times brighter. And the hypergiants, with masses of up to 150 times that of the Sun, are millions of times more luminous. This incredible and often overwhelming brightness is the source of their profound instability. They are constantly living on the edge of the Eddington limit, the critical balance point where the outward force of their own internal radiation pressure is on the verge of overcoming the inward pull of their own gravity. Imagine a star as a delicate, gravitational dance between two opposing forces. Gravity is constantly trying to crush the star, to pull all of its matter down into the center. The outward pressure of the hot gas and the radiation generated by the nuclear fusion in its core is constantly pushing back, holding the star up. In a normal star, like our Sun, these two forces are in a state of beautiful and stable equilibrium, a state that can last for billions of years. But in a hypergiant, this balance is precarious, and often it is lost. If the luminosity of a star exceeds the Eddington limit, the outward push of its radiation will literally blow its outer layers off into space. This is not a gentle, steady, stellar wind. It is a series of violent, convulsive, and often eruptive mass loss events. This is the universe's ultimate safety valve, a built-in mechanism that prevents a star from becoming infinitely massive and infinitely luminous. One of the most famous and most dramatic examples of a star that is currently and violently exceeding its Eddington limit is Eta Carinae, a truly monstrous and deeply enigmatic star system that is located about 7,500 light-years away from us, in the heart of the beautiful and spectacular Carina Nebula. Eta Carinae is thought to be a binary system, with a primary star that may have been born with a mass of up to 150 times that of our Sun, It shines with a light that is about 4 million times brighter than our Sun, a luminosity that places it firmly and dangerously in the realm of the hypergiants. And we have seen it in the act of blowing itself apart in the mid-19th century between the years 1837 and 1856. Eta Carinae underwent a massive eruptive event known as the Great Eruption. Over a period of about 2 decades, the star shed an enormous amount of mass, at least 10 to 20 times the mass of our Sun, in a series of violent outbursts. During this time, it became the second brightest star in the entire night sky. Its light so bright that it was used by sailors in the southern hemisphere for navigation. The material that was ejected in this eruption has now formed a beautiful and iconic bipolar nebula around the star, the Homunculus Nebula, a ghostly hourglass-shaped shroud of gas and dust that is still expanding outwards at a speed of over 600 kilometers per second. The cause of the Great Eruption is still not fully understood, but it was almost certainly a super-Eddington event, a moment when the star's internal luminosity so dramatically exceeded its Eddington limit that its outer layers were violently and catastrophically unbound. The mechanism by which hypergiants lose mass is a complex and still not fully understood area of astrophysics. Normal, massive stars lose mass through line-driven winds. The atoms in their outer atmospheres, particularly the metals, are very good at absorbing photons of specific wavelengths, or spectral lines. This absorption gives the atoms a little outward push, and the cumulative effect of billions of such pushes is what drives a steady and relatively gentle stellar wind. But in the extreme, and often metal-poor environments of hypergiants, this mechanism may not be sufficient to explain the staggering rates of mass loss that are observed. This has led to the proposal of other, more exotic, mechanisms. One of these is continuum-driven winds. In this scenario, the radiation field is so intense that it is not just the absorption in spectral lines that matters. The sheer, overwhelming pressure of the entire continuum of radiation is enough to push on the free electrons in the star's atmosphere, which then drag the protons along with them, creating a much more powerful and much more efficient form of mass loss. This is a particularly important idea because it could help to explain how the very first metal-free population 3 stars were able to regulate their own growth and to shed their outer layers, even in the absence of the heavy elements that are needed for line-driven winds. Another, even more speculative, idea is that hypergiants might experience deep internal explosions. In the vast convective interiors of these stars, the process of heat transfer can sometimes become inefficient, leading to the buildup of vast, superheated bubbles of plasma. These bubbles could then rise and burst through the star's surface in a series of powerful and often geyser-like eruptions. This could be a mechanism for the kind of episodic and often clumpy mass loss that is observed in stars like Eta Carinae. And there is another, curious and deeply counterintuitive concept that may be at play: the pseudo-photosphere. The photosphere is the visible surface of a star, the point at which it becomes opaque to its own radiation, but in a hypergiant with a very dense and powerful stellar wind. This visible surface may not be the true physical surface of the star at all. It may be a false surface, a pseudo-photosphere, that is formed in the optically thick wind itself, far above the star's true and much hotter surface. This could help to explain the puzzle of the yellow hypergiants, stars that are as luminous as blue hypergiants, but have a much cooler, yellow, surface temperature. Perhaps they are not truly cool stars at all. Perhaps they are hot, luminous blue variables that are currently enshrouded in a thick, cool, and opaque pseudo-photosphere, a temporary and beautiful cosmic disguise. The classification of stars is a complex, and often subtle, art. The Hertzsprung-Russell diagram, with its beautiful and orderly arrangement of stars into categories like dwarfs, giants, and supergiants, provides a powerful organizing framework, but nature is often messier and more creative than our neat, human-made categories would suggest. And nowhere is this more true than in the exotic, and often blurry, world of the hypergiants. These stars, with their extreme luminosities and their profound instabilities, often defy easy classification. They exist in a dynamic and often transitional state, and their properties can change dramatically over very short. Human timescales, the luminous blue variables, or LBVs, are a prime example of this classificatory challenge. These are massive and deeply unstable, stars that can undergo sudden, and often unpredictable, changes in their brightness, their temperature, and their spectra. In their quiescent state, they are hot, blue, and incredibly luminous, placing them in the same region of the HR diagram as the blue hypergiants. But during their eruptive phases, they can dramatically increase their brightness, and their atmospheres can become so opaque that they develop a cool pseudo-photosphere, temporarily appearing as a yellow or even a red. Supergiant. The star P Cygni is the prototype for this class, and it is a star that has been observed to change its spectral type, its temperature, and its brightness multiple times over the last few centuries. So, is an LBV a hypergiant? Or is a hypergiant an LBV? The answer is not always clear. Some astronomers consider all LBVs to be a type of hypergiant. Others argue that the term hypergiant should be reserved for those stars that show persistent signs of extreme mass loss, while the term LBV should be used for those that exhibit the characteristic eruptive variability. It is a debate that is as much about semantics as it is about physics, but it highlights the fact that these stars are living in a very unstable and very transitional phase of their lives. A similar blurriness exists at the boundary with the Wolf-Rayet stars. These are the hot, exposed, and hydrogen-poor cores of very massive stars that have already shed their entire outer envelope. One particular subclass of these, the WNL stars, are Wolf-Rayet stars that are still relatively rich in nitrogen and may still have some hydrogen remaining. These are thought to be the immediate evolutionary successors to the LBVs and the blue hypergiants. They are the stars that are on the very last step of their journey before they explode as a supernova. But even here, the lines are not always clear. Some LBVs, in their quiescent state, have been observed to have spectra that are almost indistinguishable from those of WNL stars. And some stars that were once classified as WNL stars have been seen to suddenly change their behavior and to look more like blue hypergiants. The rapid rotation of a massive star can further complicate the picture. A very rapidly rotating star can shed its outer layers so efficiently through a process of rotationally induced mixing and centrifugal mass loss that it can skip the red supergiant and the LBV phases entirely, evolving directly from a main sequence star into a Wolf-Rayet star. All of this is to say that the lives of the most massive stars are not a simple, linear, and predictable journey. They are a complex, chaotic, and beautiful dance, a story of transformations, of disguises, of sudden and violent changes. The neat categories that we have created are just a human attempt to impose order on this beautiful cosmic chaos. But the universe is not always so easily pigeonholed. And the hypergiants, in all their strange, beautiful, and unpredictable glory, are a powerful and humbling reminder that nature's creativity will always and wonderfully exceed the limits of our own human imagination. Red supergiants are the true, volumetric giants of the stellar kingdom. They are not the most massive, nor the most luminous of stars, but in terms of their sheer physical size, they are without peer. These are stars that have swelled to such colossal proportions that they could easily engulf the orbits of the inner planets of our own solar system. They are the great, bloated, and beautiful behemoths of the cosmos, stars in the final, and often dramatic, stages of their long lives. In the formal, Morgan-Keenan system of stellar classification, red supergiants are assigned to luminosity class 1, the class of the supergiants, and their red designation comes from their relatively cool surface temperatures, which place them in the K or M spectral classes, two of the most famous and most visually stunning. Examples of red supergiants are Betelgeuse, in the constellation Orion, and Antares, the brilliant, fiery heart of the constellation Scorpius. These are two of the brightest stars in our night sky, and their distinct reddish hue makes them easily recognizable, even to the casual naked eye observer. The classification of a star as a supergiant is a subtle art. It is not just a matter of its size or its total energy output. It is a spectroscopic determination, a judgment that is based on the detailed features of a star's light. The spectrum of a star is like its fingerprint, a unique pattern of dark absorption lines and bright emission lines that reveals a wealth of information about its temperature, its chemical composition, and, crucially, its surface gravity. The surface gravity of a star is a measure of how strong the gravitational pull is at its visible surface. A small, dense star, like a white dwarf, will have an incredibly high surface gravity. A large, puffy, and diffuse star, like a red supergiant, will have a very low surface gravity. And this difference in surface gravity has a direct and observable effect on the star's spectrum. In a low-gravity environment, the atoms in the star's atmosphere are less compressed, and the spectral lines they produce are narrower and sharper. By carefully measuring the width of these gravity-sensitive lines, astronomers can distinguish between a normal, main-sequence, dwarf star, a more evolved giant star, and a truly colossal supergiant star, even if they all have the same surface temperature. And even within the supergiant class, there are finer distinctions. A star can be a normal supergiant, a bright supergiant, or, in the most extreme cases, a hypergiant. The term hypergiant is, as we have seen, almost never applied to the red supergiants, with a few notable and highly unstable exceptions like VY Canis Majoris and NML Cygni. Red supergiants have surface temperatures that are relatively cool by stellar standards, typically below 4,100 Kelvin, which is cooler than our own sun. But what they lack in temperature, they make up for in size. They can have radii that are several hundred, or even more than 1,000, times that of our sun. And because their luminosity is proportional to their surface area and the fourth power of their temperature, their immense size means that they are incredibly bright. A typical red supergiant can be tens of thousands or even hundreds of thousands of times more luminous than our sun. There is, however, a theoretical upper limit to how large a red supergiant can be. This is known as the Hayashi limit. A star that expands and cools beyond this limit becomes fully convective and dynamically unstable. It can no longer maintain a state of hydrostatic equilibrium. The largest and most luminous red supergiants are thought to live right at this theoretical edge, their vast, tenuous atmospheres constantly teetering on the brink of gravitational instability. And these stars are not born this way. They are the evolved descendants of massive, hot, and blue main-sequence stars, stars that were born with a mass of between about 10 and 40 times that of our sun. As these massive stars exhaust the hydrogen fuel in their cores, they begin to burn hydrogen in a shell, which causes their outer layers to expand and cool, transforming them into the red supergiants we see today. Stars that are born with a mass of more than about 40 solar masses are so luminous that they are never able to become red supergiants at all. They shed their outer layers and evolve through a different and hotter evolutionary path. And the red supergiant phase itself is a relatively short one. A massive star will only spend a few million years in this bloated state before it exhausts its remaining nuclear fuel and ends its life in a spectacular core collapse supernova. But during this short and often turbulent phase, red supergiants play a crucial and beautiful role in the chemical evolution of the galaxy. They are prodigious losers of mass, their powerful, slow, and dense stellar winds carrying away a vast amount of material, enriched with the heavy elements that have been forged in their deep nuclear furnaces. This material, which includes carbon, nitrogen, and oxygen, is then scattered into the interstellar medium, where it will become the raw material for the next generation of stars, planets, and perhaps life. The beautiful, glowing clouds of gas and dust that we see surrounding many red supergiants. The nebulae that are the precursors to planetary nebulae are a direct and stunning visual testament to this process of cosmic recycling, a process that is essential to the ongoing creative life of the galaxy. The material that surrounds a red supergiant, the circumstellar gas and dust that has been shed from the star in its powerful stellar winds, is a rich and complex environment, a natural cosmic laboratory for studying the physics and chemistry of the interstellar medium. And one of the most fascinating phenomena that occurs in this environment is the presence of masers. A maser is the microwave equivalent of a laser. It is a source of intense, coherent, and highly directional microwave radiation. And the extended, and often dense, atmospheres of red supergiants provide the perfect conditions for these natural cosmic masers to form. They are typically produced by molecules like water vapor, silicon monoxide, and the hydroxyl radical. And they are a powerful tool for studying the properties of the circumstellar environment. By using a technique known as very long baseline interferometry, where the signals from multiple, widely separated radio telescopes are combined. Astronomers can create images of these master sources with an incredible and almost unbelievable angular resolution. This allows them to map the detailed, three-dimensional structure and motion of the gas clouds around a red supergiant, to measure the speed of the stellar wind, and even to get a direct and highly precise measurement of the star's distance through the method of parallax. This technique is revolutionizing our understanding of the mass loss process in these evolved stars, and it is helping us to build a more accurate three-dimensional map of our own Milky Way galaxy. The chemical composition of a red supergiant's atmosphere also tells a beautiful story of its deep and often hidden internal evolution. While the outer layers of the star are still mostly composed of the primordial hydrogen and helium from which it was born, the star's vast convective envelope can dredge up material from the deeper nuclear burning regions. This process brings the products of fusion, like carbon, nitrogen, and oxygen, to the surface, altering the star's atmospheric composition in a predictable and observable way. By carefully measuring the abundances of these elements in a red supergiant spectrum, astronomers can get a direct glimpse into the nuclear processes that are happening deep within its fiery heart. And the evolution of a red supergiant is not always a slow and steady process. The most massive of them can sometimes go through blue loops, temporary, and often rapid excursions on the HR diagram, where they contract and heat up to become blue supergiants before they expand and cool down again. These loops are thought to be caused by a complex interplay between the star's mass, its rotation rate, and its chemical composition, and they are a sign of the deep and often chaotic instabilities that can occur in the final stages of a massive star's life. A crucial and sometimes confusing point of classification is the distinction between a true red supergiant and a very luminous star on the asymptotic giant branch. AGB stars are the evolved descendants of lower mass stars, like our Sun. They are also large, cool, and luminous red giants, and the most massive of them can be as bright and as large as the least massive red supergiants. But they have a fundamentally different internal structure and a very different ultimate fate. A true red supergiant is a massive star that will go on to fuse heavier and heavier elements in its core, eventually forming an iron core and exploding as a core collapse supernova. An AGB star, on the other hand, has an inert carbon-oxygen core, and it will end its life by shedding its outer layers to form a planetary nebula, leaving behind a white dwarf. The distinction between these two classes of stars is a subtle but important one, and it highlights the fact that nature does not always fit into our neat and often oversimplified classificatory boxes. But for the true red supergiants, the end is always the same, and it is always spectacular. After a life that is measured in the millions, not the billions, of years, after a long and often turbulent journey across the HR diagram, after having enriched the galaxy with the heavy elements that will one day form new stars and new worlds, the iron core of a red supergiant finally and catastrophically collapses. In a fraction of a second, the star is gone, its immense mass and energy released in a single, brilliant, and universe-shaking flash of light. A supernova explosion that will briefly and beautifully outshine its entire host galaxy. It is a final and spectacular act in the life of a true cosmic giant, a final gift to the ongoing, creative, and beautiful story of the cosmos. A subgiant is a star that is in a fascinating and often fleeting transitional phase of its life. It is a star that has exhausted the hydrogen fuel in its core and has begun its journey away from the stable, long-lived main sequence and towards its ultimate fate as a giant star. It is, in a sense, a star in its adolescence, a star that is no longer a child, but not yet a full-grown adult. The term subgiant has two related meanings in astronomy. It refers to a specific luminosity class in the Morgan-Keenan system of stellar classification, a class of stars that are more luminous than main sequence dwarfs, but less luminous than true giants. And it also refers to a specific evolutionary stage in the life of a low to intermediate mass star. The subgiant phase begins at the moment that a star's core ceases to fuse hydrogen. Without the outward pressure of fusion to support it, the now inert helium core begins to contract and heat up under its own gravity. This, in turn, heats up the shell of hydrogen that surrounds the core, causing it to ignite and to begin fusing hydrogen into helium in a thin and often intense shell. The energy from this new shell-burning source causes the star's outer layers to expand and cool. On the Hertzsprung-Russell diagram, the star's evolutionary track moves horizontally to the right, towards the cooler, redder side of the diagram, while its luminosity stays roughly constant, or even increases slightly. This horizontal track is known as the subgiant branch. The duration of this subgiant phase depends on the star's mass. For a star like our Sun, it will last for a few 100 million years. For more massive stars, it can be much shorter, only a few million years. This is why subgiants are relatively rare in the sky. We are simply not likely to catch a star in this brief transitional phase. As the hydrogen-burning shell continues to add more helium ash to the core continues to grow in mass and to contract. Eventually, for a star like our Sun, the core will become so dense that it is no longer supported by normal gas pressure, but by the strange quantum mechanical force of electron degeneracy pressure. At this point, the star's evolution accelerates dramatically. The degenerate core heats up, the hydrogen-burning shell becomes even more intense, and the star's outer convective envelope expands rapidly, causing the star to move almost vertically up the HR diagram, on a path known as the red giant branch. The subgiant phase is a crucial and often complex turning point in a star's life, and its detailed behavior depends sensitively on the star's initial mass and chemical composition. For stars with a mass less than about 2 solar masses, the transition from the main sequence to the red giant branch is a relatively smooth one. But for more massive stars, the transition is more dramatic. The helium core can grow so massive that it exceeds a critical limit, the Schoenberg-Chandrasekhar limit, even before it becomes degenerate. This triggers a rapid collapse of the core and a rapid expansion and cooling of the outer layers, causing the star to move very quickly across the HR diagram. This rapid evolution is what creates the Hertzsprung gap, a sparsely populated region of the HR diagram that is often seen in the color magnitude diagrams of intermediate-age star clusters. Some subgiants, as they make their journey across the HR diagram, can pass through a region known as the instability strip. In this region, the star's atmosphere becomes unstable to pulsations, causing the star to rhythmically expand and contract, and to vary in brightness. These pulsating subgiants are known as delta Scuti variables, and in a few rare cases, even more massive stars can become classical Cepheid variables during their brief subgiant phase. The study of subgiants is a crucial tool for astronomers. Because the subgiant phase is so short, the point at which stars in a cluster turn off the main sequence and move on to the subgiant branch is a very precise indicator of the cluster's age. By carefully modeling the subgiant branches of globular clusters, astronomers can determine their ages with incredible precision, which in turn allows us to place a lower limit on the age of the universe itself. And in recent years, with the advent of high-precision exoplanet detection techniques, we have even begun to find planets orbiting subgiant stars. These discoveries are providing us with a fascinating and often surprising new window into the late stages of planetary system evolution, showing us what might happen to a planetary system when its central star begins to die. The subgiant phase is a fleeting, but beautiful, and deeply informative chapter in the life of a star. It is a moment of profound and often dramatic transformation, a bridge between the long, quiet stability of the main sequence and the final, brilliant, and often spectacular glory of the giant phase. Betelgeuse, the great crimson jewel of the winter sky, is more than just a beautiful star. It is a cosmic laboratory, a nearby and accessible example of one of the most extreme and most important types of objects in the universe: a red supergiant. Its sheer size, its profound instability, and its impending and spectacular death make it an object of intense and enduring fascination for both professional astronomers and amateur stargazers alike. It is a star that is, in a very real sense, living on borrowed time, and in its slow and often dramatic death throes, it is teaching us a great deal about the life and death of the most massive stars in the cosmos. Betelgeuse is a semi-regular variable star, its brightness changing in a complex and not fully understood rhythm. There seems to be a primary period of about 400 days, which is thought to be related to the fundamental radial pulsation of the star's vast convective envelope. But there are also other longer-term cycles, and a great deal of irregular, chaotic variability superimposed on top of these. This complex variability is a sign of the deep and often violent instabilities that are at play in the heart of this dying giant. In late 2019, Betelgeuse underwent a dramatic and unprecedented dimming event, its brightness dropping by a factor of almost 3. This great dimming sparked a flurry of speculation, both in the scientific community and in the popular press. Was this the prelude to a supernova? Was the demon star finally about to explode? The answer, it turned out, was more subtle, but no less fascinating. High-resolution images from the Hubble Space Telescope and the Very Large Telescope revealed that the dimming was not caused by a change in the star's intrinsic luminosity, but by a vast cloud of dust that had been ejected from the star's surface and was temporarily obscuring our view. Betelgeuse had, in a sense, sneezed. It had undergone a surface mass ejection, a localized and powerful eruption that had flung a huge amount of its own atmospheric material out into space. As this material traveled outwards and cooled, it condensed into a thick cloud of silicate and carbon dust, a temporary and beautiful cosmic veil. This event was a stunning confirmation of a long-held theory that the mass loss from red supergiants is not a smooth, steady process, but is often clumpy, episodic, and driven by the violent, convective, and magnetic activity on the star's surface. The sheer physical size of Betelgeuse is almost impossible to comprehend. Its radius is thought to be about 764 times that of our Sun. This is a number that is so large it almost loses its meaning. But if you were to place Betelgeuse at the center of our solar system, its roiling, crimson surface would extend out past the orbit of the asteroid belt and would be dangerously close to the orbit of Jupiter. It is a star of truly colossal proportions, and yet, for all its size, it is not particularly massive. Its current mass is estimated to be somewhere between 16 and 19 times the mass of our Sun. This means that its average density is incredibly, almost absurdly, low, thousands of times less dense than the air in the room you are in. It is a vast, tenuous, and ghostly behemoth. And it is a young star. In cosmic terms, it is thought to be only about 8 to 8.5 million years old. But because of its immense initial mass, it has burned through its nuclear fuel at a furious pace and has already evolved off the main sequence and into its final red supergiant phase. And it does not have much time left. Astronomers estimate that Betelgeuse will end its life in a spectacular core collapse supernova sometime in the next 100,000 years. When this happens, it will be the astronomical event of a lifetime, and perhaps of a millennium. It will be the closest supernova to Earth to have been observed since the invention of the telescope. At its peak, it will shine with a brightness that could rival that of the full moon, a single, brilliant point of light that will be easily visible in the daytime sky. It will be a spectacular and beautiful final farewell from one of our most beloved and most enigmatic celestial neighbors. And in its death, it will give a final and profound gift to the cosmos. The heavy elements that have been forged in its deep nuclear furnace, the carbon, the oxygen, the silicon, the urine will be scattered into the interstellar medium, enriching the cosmic gas clouds from which a new generation of stars, of planets, and perhaps of life will one day be born. Betelgeuse is more than just a star. It is a story of life, of death, of transformation, and of the deep, beautiful, and endless cycle of cosmic creation and renewal. The classification of stars into different populations is one of the most fundamental and most powerful organizing principles in modern astronomy. It is a system that allows us to read the history of the universe in the light of the stars themselves. The story begins, as we have seen, with Walter Baade in the 1940s, and his realization that the stars in our galaxy could be divided into two broad categories. Population 1 stars, like our own Sun, are found in the disk of the galaxy. They are relatively young, and they are rich in metals, Population 2 stars, on the other hand, are found in the galaxy's central bulge and its surrounding spherical halo. They are ancient, and they are very poor in metals. This simple observational distinction tells a profound story of cosmic chemical evolution. The universe, in its infancy, was a very simple place, made almost exclusively of the light elements, hydrogen and helium, that were forged in the Big Bang. The very first stars to form in this primordial gas, the hypothetical population 3 stars, were therefore completely metal-free. These stars were likely incredibly massive, and because of their lack of metals, which act as an efficient cooling agent in modern star formation, they were able to grow to sizes that are almost unimaginable today, perhaps hundreds of times the mass of our Sun. And because of their immense mass, they lived incredibly fast and died incredibly young. They're spectacular and often universe-shaping. Lives ending in powerful supernova explosions after only a few million years. It was in the fiery and often violent deaths of these first population 3 stars that the first heavy elements were forged. The carbon, the oxygen, the iron, the silicon, all the elements that are essential for the formation of rocky planets and for the chemistry of life, were created in these primordial stellar furnaces and then scattered into the interstellar medium. The next generation of stars, the population 2 stars, were born from this slightly and beautifully enriched gas. They are the true ancient elders of our galaxy, stars that are over 10 billion years old. They have a low, but non-zero, metal content, a faint chemical echo of the first stars that came before them. And they, in turn, through their own, long and often dramatic, stellar lives, continued this process of cosmic alchemy. As they aged and died, they released even more metals into the surrounding space, further enriching the cosmic gas clouds. And so, with each successive generation of stars, the metal content of the galaxy has steadily increased. Our own population Y Sun, a relative newcomer to the galactic stage, born a mere 4.6 billion years ago, is the product of this long and patient process of cosmic recycling. Its relatively high metal content, about 1.4% of its total mass, was the essential and non-negotiable prerequisite for the formation of our own solar system. Without the metals from countless generations of long-dead stars, there would be no rocky planets, no Earth, no life, no us. We are, in the most literal and profound sense, the children of the stars, the atoms in our bodies, the iron in our blood, the calcium in our bones, the oxygen we breathe, were all forged in the fiery hearts of stars that lived and died long before our Sun was even born. The search for the elusive. Population 3 stars is one of the great and most challenging quests in modern astronomy. We will likely never see one of these primordial giants directly in our own galaxy. They are all long gone. But we are now, for the first time, with the incredible deep time-seeing power of the James Webb Space Telescope, able to look back to the very edge of the observable universe, to the cosmic dawn, and to search for the faint, red-shifted light of the very first galaxies, the galaxies that were built from and lit up by these first, magnificent, and universe-shaping stars. The life of a star is a delicate and often dramatic balancing act for millions, billions, or even trillions of years. A star is in a state of hydrostatic equilibrium, a beautiful and stable dance between two immense and opposing forces. On the one hand, there is the relentless inward crush of its own gravity, constantly trying to pull all of its matter down into a single, infinitely dense point. On the other hand, there is the powerful outward push of the pressure generated by the nuclear fusion reactions in its hot, dense core. As long as these two forces are in balance, the star is stable, shining with a steady and often life-giving light. But this balance is a temporary one. A star is a finite system with a finite amount of nuclear fuel. And when that fuel begins to run out, the star's long and often peaceful. Life enters its final and often spectacular act. The story of stellar evolution is, at its heart, the story of this battle and of what happens when the fires of fusion begin to flicker and die. All stars are born from the gravitational collapse of vast cold clouds of interstellar gas and dust. As a clump of this material collapses, it heats up, forming a hot, dense, and glowing protostar. As it continues to accrete more material, its core temperature and pressure continue to rise until it reaches a critical threshold of about 10 million degrees Kelvin. At this point, the nuclear furnace ignites. Hydrogen atoms begin to fuse together to form helium, releasing a tremendous amount of energy in the process. This is the birth of a true star. The outward pressure of this new and powerful energy source halts the gravitational collapse, and the star settles into the long, stable, and hydrogen-burning phase of its life, the main sequence. The star's position on the main sequence is determined almost entirely by its initial mass. Low-mass stars, like the red dwarfs, are small, cool, and dim. They burn their hydrogen fuel incredibly slowly and can live for trillions of years. High-mass stars, like the hot blue O-type stars, are large, hot, and incredibly luminous. They burn through their fuel at a furious pace and live for only a few million years. Our own sun, a modest, yellow, G-type star, sits comfortably in the middle, with a main sequence lifetime of about 10 billion years. But eventually, for all stars, the hydrogen fuel in the core runs out, and this is where their evolutionary paths diverge dramatically. For a low-mass star, like our sun, the now inert helium core begins to contract and heat up. Hydrogen fusion ignites in a shell around this core, which causes the star's outer layers to expand and cool. The star becomes a red giant. Eventually, the core becomes hot and dense enough to ignite the fusion of helium into carbon. After this helium-burning phase, the star is not massive enough to ignite the fusion of carbon. Its nuclear life is over. It sheds its outer layers, creating a beautiful, glowing planetary nebula. And its hot, dense, carbon-oxygen core is left behind to slowly cool and fade as a white dwarf. For a high-mass star, the story is far more violent. After the red supergiant phase, its core is massive enough to continue the process of nuclear fusion, creating a series of nested, onion-like shells of heavier and heavier elements: helium, carbon, oxygen, neon, silicon, and finally, iron. The fusion of iron does not release energy, it consumes it. The nuclear furnace has been extinguished. Gravity wins its long and patient battle. The iron core collapses catastrophically in a fraction of a second, triggering a titanic core collapse supernova explosion that can briefly outshine an entire galaxy. What is left behind is either an incredibly dense neutron star, or, if the progenitor star was massive enough, a black hole, an object whose gravity is so strong that not even light can escape. This is the grand and beautiful cycle of stellar life and death, a cycle that has, over the 14 billion-year history of the universe, transformed the simple, primordial gas of the Big Bang into the rich and complex chemical tapestry that makes up our world and ourselves. When a star like our sun reaches the end of its life, it does not go out with a bang, but with a long, slow, and beautiful sigh. The process begins when the hydrogen fuel in its core is exhausted. The star, no longer able to support itself against the inward crush of its own gravity, begins a series of profound and dramatic transformations. The now inert helium core contracts and heats up. This, in turn, heats the shell of hydrogen that surrounds the core, causing it to ignite and to begin fusing hydrogen into helium at a furious rate. The immense energy released by this shell-burning source pushes the star's outer layers outwards, causing the star to swell to hundreds of times its original size. As it expands, its surface cools, and its color changes from a gentle yellow to a deep and brilliant red. The star has become a red giant. This is the fate that awaits our own sun in about 5 billion years. It will expand to engulf the orbits of Mercury and Venus, and it will likely vaporize the oceans and atmosphere of our own beloved Earth. But the story is not over. As the star continues on its red giant path, the helium core continues to contract and heat up. Eventually, for a star like our Sun, it will reach a temperature of about 100 million Kelvin. At this point, a new and even more powerful nuclear fire is ignited the fusion of helium into carbon. For a low-mass star, this ignition is a sudden and violent event known as a helium flash. The core is in a strange, degenerate state, and the fusion reaction spreads through it in a matter of hours, releasing a tremendous amount of energy. But this explosion is buried deep within the star's interior, and its effects on the outside are surprisingly gentle. The star contracts, its surface heats up, and it settles into a new, stable phase of its life, the horizontal branch, where it calmly fuses helium in its core for another 100 million years or so. But this, too, is a temporary reprieve. Eventually, the helium in the core is also exhausted, leaving behind an inert core of carbon and oxygen. The star then begins its second ascent up the giant branch, a phase known as the asymptotic giant branch. It is now a truly colossal and deeply unstable object, with two nested fusion shells, an inner helium-burning shell and an outer hydrogen-burning shell. In this final and often turbulent phase, the star undergoes a series of thermal pulses, powerful and often chaotic. Flashes of the helium-burning shell that cause the star to pulsate and to shed its outer layers in a series of powerful stellar winds. Eventually, the entire hydrogen-rich envelope of the star is blown away into space, creating a beautiful, glowing, and often intricate cloud of gas and dust, a planetary nebula. At the center of this expanding and often short-lived cosmic jewel lies the hot and incredibly dense remnant of the star's core, a white dwarf. A white dwarf is a stellar corpse, an object that is no longer generating energy through nuclear fusion. It shines only with its own residual heat, a heat that will take billions and even trillions of years to radiate away. It is an object of incredible density, with the mass of a sun packed into a volume the size of the Earth. A single teaspoon of its material would weigh as much as a truck. It is supported against the final, and otherwise inevitable, crush of gravity by electron degeneracy pressure, a quantum mechanical force that arises from the fact that electrons are fermions and cannot be squeezed into the same quantum state. But even this powerful quantum pressure has its limits. If a white dwarf accretes enough mass from a binary companion to push it over the Chandrasekhar limit of about 1.4 solar masses, it will explode as a spectacular Type Ia supernova. But if it is left to its own devices, it will simply cool, and cool, and cool, until after a time far longer than the current age of the universe, it will become a cold, dark, and eternally silent black dwarf, a final and invisible monument to the long, beautiful, and ultimately gentle life of a sun-like star. The universe, in its grand and often violent unfolding, is a place of almost unimaginable extremes, and nowhere are these extremes more apparent than in the strange, beautiful, and often terrifying objects that are left behind after the death of the most massive stars. When a star with more than about 8 times the mass of our Sun exhausts its nuclear fuel, its iron core collapses catastrophically, triggering a core collapse supernova explosion that can briefly outshine an entire galaxy. But what is left behind in the heart of this cosmic cataclysm? The answer depends on the precise mass of the collapsing core. If the core is not too massive, typically less than about 2 to 3 times the mass of our Sun, the collapse will be halted by neutron degeneracy pressure. This is a quantum mechanical force, similar to the electron degeneracy pressure that supports a white dwarf, but much, much stronger. The immense pressure in the collapsing core is so great that it forces the electrons to merge with the protons, creating a super-dense ball of almost pure neutrons. This is a neutron star. It is an object of almost unbelievable density. It packs the mass of 1.5 suns into a sphere that is only about 20 kilometers in diameter, the size of a large city. A single, sugar cube-sized piece of neutron star material would weigh as much as all of humanity combined. The gravitational pull at its surface is hundreds of billions of times stronger than that of the Earth. And as the progenitor star's core collapses, the conservation of angular momentum causes the neutron star to spin at an incredible rate, often hundreds of times per second. This rapid rotation, combined with the star's incredibly strong magnetic field, can turn the neutron star into a pulsar, a cosmic lighthouse that sweeps 2 powerful beams of radiation across the galaxy. But if the collapsing core is even more massive, if it exceeds the Tolman-Oppenheimer-Volkoff limit of about 2 to 3 solar masses, then not even the immense and almost incompressible force of neutron degeneracy pressure can halt the final and otherwise inevitable gravitational collapse. The core continues to shrink, its density and its gravitational pull increasing without limit, until it crushes itself into a black hole, an object whose gravity is so strong that it warps the very fabric of space-time around it into a one-way membrane, an event horizon from which nothing, not even light itself, can escape. The existence of black holes is one of the most profound and most beautiful predictions of Einstein's general theory of relativity, and it is a prediction that has now been confirmed with a wealth of observational evidence from the dance of the stars that orbit the supermassive black hole at the center of our own galaxy, to the direct detection of the gravitational waves that are emitted when 2 black holes collide and merge. The interior of a black hole is a realm where our current laws of physics break down. General relativity predicts a singularity at its center, a point of infinite density and infinite space-time curvature. But this is almost certainly a sign that the theory is incomplete. A full theory of quantum gravity is needed to understand what truly happens at the heart of a black hole. But what we do know is that a black hole is a final and absolute end state. It is a cosmic prison, a place where matter, energy, and information are seemingly lost to the outside universe forever. The story of stellar remnants, of white dwarfs, of neutron stars, of black holes, is a story that is told in the language of the most extreme physics imaginable. It is a story of quantum mechanics, of general relativity, of nuclear physics, of gravity pushed to its absolute limits, and it is a story that is still being written. The details of the supernova explosion mechanism, the precise dividing lines between the different possible end states, the nature of the matter in the core of a neutron star, these are all active and exciting areas of research, but the broad outlines of the story are clear. And it is a story that is crucial to our own existence, for it is in the fiery and often violent, deaths of the most massive stars that the heavy elements that make up our world, and ourselves, are forged and scattered into the cosmos. We are, in the most literal sense, the children of supernova, the recycled ashes of long-dead stars, given a second and far more beautiful life. In the vast and often imaginary Cosmic Hall of Fame, a special place of honor must be reserved for the true heavyweight champions of the stellar kingdom, the colossal and often enigmatic stars that are known to astronomers as the red supergiants. And among these, one star in particular has long held the title of the biggest, the baddest, and the most mysterious of them all, the behemoth, WOH G64. This is not just a big star, it is a star of almost mythological proportions, a star that seems to be actively and gleefully breaking the very rules that are supposed to govern the lives of stars. It is a star that is located not in our own familiar Milky Way, but in our nearest and much wilder galactic neighbor. The Large Magellanic Cloud, WOH G64, was first identified in the 1970s by a trio of astronomers, Westerlund, Olander, and Hesser, whose names are now immortalized in the star's official designation. And from the very beginning, it was clear that this was not an ordinary star. Its immense size and its incredible brightness were immediately apparent. Modern estimates suggest that its radius is about 1,540 times that of our Sun. This is a number that is difficult to wrap the human mind around. But if you were to replace our Sun with WOH G64, its fiery and bloated surface would extend out past the orbit of Jupiter, engulfing all of the inner rocky planets and the asteroid belt in a single fiery gulp. And its luminosity is no less staggering. It is thought to be shining with the light of about 280,000 suns, making it one of the most luminous, cool supergiants known. But for all its brilliance, we cannot see this star with our own eyes. It is shrouded in a thick and often impenetrable cocoon of gas and dust, a toroidal or donut-shaped nebula that it has itself created. This dusty veil is a telltale sign that WOH G64 is a star in the final and most turbulent stages of its life. It is actively and violently shedding its outer layers, blowing them off into space in a powerful and often chaotic stellar wind. This circumstellar material, which extends for over a light year from the star, is a testament to the profound instabilities that are at play in the heart of this dying giant. And here is where the story gets even stranger. For a star of its immense size and luminosity, WOH G64 is surprisingly, and almost impossibly, cool. Its surface temperature is only about 3,400 Kelvin. This places it in the realm of the red supergiants, but it also places it at, or even beyond, the Hayashi limit, a theoretical boundary on the HR diagram to the right of which a star of a given mass cannot exist in a state of stable hydrostatic equilibrium. WOH G64 is, in a very real sense, a star that should not exist. This has led to a number of fascinating and often speculative theories. Is it really a single star, or could it be a close, and as yet unresolved, binary system, with a more massive and hotter companion star that is hidden from our view? The presence of a companion could help to explain the star's extreme mass loss, its unusual chemistry, and its location in a seemingly forbidden region of the HR diagram. Or is it something else entirely? Could it be a Thorne-Zhitkov object, a bizarre and still hypothetical type of star where a neutron star has been swallowed by and has spiraled into the core of a red supergiant? The physics of such an object would be incredibly complex, and it could, in principle, lead to the kind of extreme luminosity and instability that we see in WOH G64. The location of the behemoth, in the metal-poor environment of the large Magellanic Cloud, is another crucial clue. The lower abundance of heavy elements in the LMC is thought to allow stars to grow to much larger masses and sizes than they can in our own, more metal-rich Milky Way. WOH G64 may be a living and soon to be dying example of the kind of primordial, monster stars that were common in the early and much wilder days of the universe. It is a cosmic fossil, a window into a time when the universe was a more extreme and more creative place. WOH G64 is more than just a big star. It is a puzzle, a paradox, and a profound mystery. It is a star that is challenging our most basic and most cherished models of stellar evolution, and in its strange, beautiful, and ultimately self-destructive glory. It is a powerful reminder that the universe is still full of surprises, and that the true cosmic monsters are often far stranger and far more magnificent than anything we could have ever imagined.